There's a beacon out there in the galaxy, a strange, cosmic lighthouse that spins in silence, never sending a radio pulse, never cracking through our telescopes in the way most of its kind do. But it sings. It sings in the highest, most energetic wavelengths we can detect, gamma rays and X-rays, blinking with regularity like a ghost signaling across the abyss of space. This is the Geminga pulsar, and it's one of the most peculiar, mesmerizing, and scientifically frustrating stellar remnants in the known universe. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Imagine a star that once lived large, a giant, burning sphere that ended in catastrophic collapse, dying in a supernova that briefly outshone its galaxy. What remains is no longer a typical star, but a neutron star, a city-sized core of atomic debris, crushed under such extreme gravity that the very idea of matter is redefined. Among these strange relics of dead stars, some of them are gifted, or cursed, with a bizarre trait: they emit beams of energy as they spin. These are pulsars, cosmic metronomes flashing signals out into space. Most of them can be heard, with radio telescopes, crackling, rhythmic beacons ticking like clocks across cosmic time. But not Jaminga. Jaminga doesn't speak in radio. It's silent, like a phantom. For decades, it stood out like a sore thumb in the sky, blazing in gamma rays, mysterious in form, its location vague, its identity unknown. It was once called a gamma ray source, with no known explanation. It was as though the universe had struck a tuning fork in the darkness and let it ring out in energy we could barely perceive, but we could not understand from where or why. Then slowly, through decades of cross-disciplinary astrophysical detective work, the truth began to unfold. What we now know is both awe-inspiring and confounding. This is a neutron star unlike almost any other. One that defies the rules. One that demands we ask new questions. Why does it glow only in gamma rays? Why can't we detect it in radio? What hides within its magnetosphere? Is it an outlier, or a window into an entire hidden population of radio-silent neutron stars that have simply gone unnoticed? Jaminga is more than just a mystery. It's a scientific frontier, a place where old assumptions are challenged, and new physics might be waiting to emerge. At only about 800 light-years from Earth, it's practically in our galactic backyard, which makes its silence all the more haunting. This is no distant enigma at the edge of the observable universe. This is a neighbor with a secret. We live in a universe that often screams through black holes, solar flares, and violent births and deaths of stars. But occasionally it whispers. It whispers in gamma rays. And that whisper has a name, Jaminga. After first encountering the cryptic presence of Jaminga, to truly understand why it's so strange, we must take a step back into the realm of neutron stars and the extraordinary subset known as pulsars. Pulsars are not just any leftover pieces of stellar death. They are, quite literally, spinning beacons of physics pushed to its edge. They are neutron stars that rotate rapidly, possessing intense magnetic fields and emitting beams of electromagnetic radiation from their magnetic poles. Think of a lighthouse by the sea, casting its beam across dark waters, rotating on a predictable rhythm. Pulsars work in a similar fashion, but on a cosmic scale and with unimaginable power. A neutron star itself is already an extreme object. Formed when a massive star goes supernova, what's left behind is a core so dense that atoms themselves collapse, electrons and protons fuse into neutrons, and a teaspoon of the material would weigh more than a mountain on Earth. Crushed into a sphere barely 20 kilometers wide, the neutron star retains all the angular momentum of its former massive self. This conservation of momentum means that what was once a slow-spinning star now whirls around at dizzying speeds, sometimes multiple times per second. In a pulsar, the magnetic axis of the neutron star is not aligned with its rotational axis. That means as it spins, the beams of radiation emitted from its magnetic poles sweep across the sky. If Earth happens to lie in the path of these sweeping beams, we observe a periodic flashing signal, like a cosmic heartbeat, timed down to milliseconds with a consistency unmatched by even our best atomic clocks. These pulses are typically observed in the radio portion of the spectrum. It's how pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. The first one appeared as an astonishingly regular set of radio pulses, so precise that for a brief moment, some scientists even wondered if it might be a signal from an alien civilization. They called it LGM-1, for Little Green Men. Of course, it turned out to be something far more profound, the universe speaking through the remnants of dead stars, timing their pulses across the cosmos like a metronome set by nature itself. Most known pulsars emit primarily in radio waves. That's how we find them, radio telescopes scanning the skies, catching the rhythmic blips of these spinning corpses. The pulses can range in frequency from seconds to milliseconds. Millisecond pulsars, in particular, spin incredibly fast, hundreds of times per second, and are thought to have been recycled by accreting matter from a companion star, spinning them up like celestial flywheels. But pulsars don't only emit in radio. Some of them shine across a wider spectrum, including visible light, ultraviolet, X-rays, and even gamma rays. The nature of this emission depends on the particle interactions in their magnetospheres, the acceleration of electrons and positrons, and the intricate dance of magnetic field lines twisted by relativistic rotation. Still, the most reliable way to discover them has long been through radio astronomy. The pulses are unmistakable, predictable, and penetrating. They travel vast distances with minimal interference. That's why when we find a neutron star that doesn't emit in radio, or emits so faintly that it escapes detection, we're forced to confront deeper, more complex questions about the structure and orientation of its magnetic fields, the physics of its emission mechanisms, and even our own observational biases. So when Jaminga was first found glowing in gamma rays without any corresponding radio signal, it was as if someone had taken the bell away from a clock tower, leaving only the faint glimmer of candlelight behind. It disrupted our expectations and forced scientists to look at pulsars in an entirely new way. Could we have missed others like it? Have we been listening only to the loudest members of a much larger and more diverse population of stellar remnants? Jaminga represents a class of objects that emit their pulses not in the well-traveled frequency bands of radio waves but in the rarefied upper energy ranges, places where only specialized instruments can see. To understand just how much of an outlier this made it, we have to dive into its discovery, a tale that stretches across decades, satellites, and a scientific community both puzzled and obsessed by a ghost that blinked in gamma. The remarkable thing about pulsars is how unmistakably loud they usually are, at least in a specific way. When we speak of the standard pulsar signature, we're referring to that crisp, rhythmic pulse of radio waves that most neutron stars emit, detectable from across the galaxy. It's this radio heartbeat that made pulsars famous, and it remains the primary tool for identifying them even decades after their discovery. These radio pulses are not random bursts of noise but tightly timed, periodic signals, often accurate to microseconds. Some pulsars, like the famous millisecond pulsars, are so precise they rival atomic clocks in their stability. When early astronomers like Jocelyn Bell Burnell were first scanning the skies with radio telescopes in the 1960s, the signals they found from what would become known as pulsars seemed eerily artificial. The first detection, a series of evenly spaced blips, had no known natural explanation at the time. Each tick of the pulsar came precisely 1.337 seconds apart. This led to the initial, half-joking speculation that the signals might be from extraterrestrial intelligence. But as more of these signals were discovered, a pattern emerged. These weren't alien broadcasts. They were the rotational signatures of something far more exotic, neutron stars acting like cosmic lighthouses. The process works like this. As a neutron star spins, its powerful magnetic field channels high-energy particles along its magnetic poles, creating intense radiation. This radiation, usually in the form of radio waves, shoots outward in narrow beams. Because the star's magnetic axis is typically misaligned with its rotation axis, the beams sweep around like a lighthouse. If Earth happens to lie in the path of this beam, we see a pulse every time the beam sweeps past us. And because these objects rotate so predictably, the result is a stable, periodic signal that can be tracked with incredible accuracy. The result is that most of the thousands of pulsars catalogued to date have been found using radio telescopes. Instruments like the Arecibo Observatory, before its collapse, the Parkes Radio Telescope in Australia, and the Green Bank Telescope in West Virginia have scanned the skies for these radio flashes. Surveys such as the Parkes Multibeam Pulsar Survey and more recently, Loafer and Chime, have dramatically increased the number of known pulsars by listening for these characteristic signatures. This reliance on radio detection has shaped our entire understanding of what a pulsar should look like. Radio waves penetrate dust and gas with ease, travel across immense distances with little distortion, and are easily detectable with ground-based equipment. When astronomers see these signals, they can measure not only the pulse period, how long it takes for one full rotation, but also how that period changes over time. This reveals the pulsar's age, magnetic field strength, and even interactions with companion stars or surrounding matter. In fact, many pulsars exhibit a regular slowdown in their rotation over time, caused by the loss of rotational energy through the emission of radiation and particles. This spin-down rate provides crucial clues about the age and energy of the pulsar. Combined with the pulse profile, the shape of the radio signal as it rises and falls, astronomers can infer the geometry of the neutron star, the orientation of its beams, and the behavior of its magnetic field. So this standard signature, a repeating pattern of radio pulses, is not just a means of detection. It's a window into the heart of these stellar remnants. It allows us to time their rotation, model their internal structure, test the limits of general relativity, and even detect planets orbiting them. The discovery of the first exoplanets, in fact, came from timing irregularities in a pulsar's radio pulses. But with all this in mind, Jaminga stood out like a whisper in a room full of shouting. Here was an object exhibiting all the hallmarks of a pulsar: regular timing, intense energy output, but none of the usual radio fingerprints. It was, as far as early observers could tell, invisible to the instruments that had built our pulsar catalog. It blinked in a light we rarely used to search for such objects, gamma rays, and it did so silently, defying decades of observational precedent. If radio pulses are the language through which most pulsars communicate with us, Jaminga seemed to be speaking a different dialect entirely, one that required new tools, new ideas, and a reevaluation of how pulsars can behave. It didn't just challenge the standard model, it forced astronomers to ask, what if our understanding is limited by what we're able to hear? For decades, astronomers swept the skies with radio telescopes, listening for the ticking heartbeats of pulsars. These were the standards, beacons that screamed across the cosmos, cutting through interstellar dust, arriving with reliable precision. The rhythm of these dead stars was clear, confident, and expected. And then, amidst this familiar chorus of cosmic metronomes, something strange appeared. Not a voice, but a shimmer. A ghostly glimmer of energy at the highest frequencies, gamma rays, appearing and reappearing with a curious regularity. But it had no radio companion. No ticking. No voice. This was Jaminga, a silent oddity among a crowd of talkative cousins. It first made its presence known in the 1970s, though not in the traditional sense. It wasn't seen or heard, it was felt in a way. Instruments aboard NASA's SAS-2 satellite, designed to detect gamma rays, picked up a mysterious, bright source of high-energy radiation in the constellation Gemini. This source didn't move like a planet, didn't vary like a quasar, and didn't match any known celestial object. It was just there, steady, persistent, but cloaked in anonymity. Its energy was unmistakable, powerful gamma rays, some of the most energetic photons in the universe. But unlike all the pulsars astronomers had catalogued up to that point, this one gave off no radio signals. It was a new kind of problem. A bright puzzle. A loud enigma that made no sound. To fully appreciate how jarring this was to the scientific community, you have to understand the context. At the time, the toolkit for identifying neutron stars and pulsars was largely based on radio astronomy. The idea of a pulsar that didn't emit in radio, at least not detectably, was like discovering a lighthouse that glowed in ultraviolet but never flashed visible light. It wasn't supposed to happen. Yet here was Jaminga, standing in defiance of expectations, almost teasing the scientists who studied it. The mystery deepened over the years. The gamma-ray emission wasn't sporadic, it was stable, periodic. It hinted at rotation. It behaved, in many ways, exactly like a pulsar. But without a radio signature, confirming that hypothesis proved maddeningly difficult. Over the years, astronomers tried to match the gamma-ray source with objects in other wavelengths, optical, X-ray, infrared, radio, but nothing seemed to line up. This wasn't a conventional neutron star. This wasn't even clearly a star at all. It was just a point of energy, no clear location, no optical counterpart, and no fingerprint. Jaminga's silence became its most defining trait. The absence of radio waves wasn't just a gap in the data. It was a problem that echoed through theoretical models. Could a neutron star emit only gamma rays? Was that even possible? Had our understanding of pulsars been limited all along by the narrow band of electromagnetic radiation we had chosen to observe? These questions loomed large, and Jaminga sat at the center of them, an object too strange to ignore but too obscure to explain. The object's persistent gamma-ray brightness gave it away as something incredibly energetic. Only the most extreme astrophysical environments produce gamma rays. The interiors of active galactic nuclei, supernova remnants, black hole accretion disks, and yes, neutron stars. But neutron stars almost always give away their presence in radio. Not this one. This one was cloaked. And as more sensitive instruments were deployed over the years, including ESA's Caspi satellite and later NASA's Compton Gamma Ray Observatory, Jaminga's gamma-ray glow remained prominent, yet still unaccompanied by a radio voice. The mystery grew famous within the astrophysical community. It wasn't just another unidentified source. It was the unidentified source. So enigmatic that it became a standard example in textbooks and conferences of what we didn't yet understand. It was often referred to as one of the brightest persistent gamma-ray sources in the sky, yet it defied classification. It forced astronomers to question how many other such sources might exist, pulsars hidden in the high-energy end of the spectrum, invisible to traditional surveys. Then came a turning point. In the early 1990s, the Rosat X-ray Observatory added a critical piece to the puzzle. Rosat was designed to scan the sky in X-rays, a slightly less energetic but still high-frequency form of light. And it saw something that matched Jaminga's coordinates. A faint, flickering source of X-rays in the same region as the gamma-ray anomaly. More than that, the X-rays appeared to pulse. This was a breakthrough. For the first time, astronomers could say with greater confidence that the source was indeed a neutron star. The periodicity in the X-ray data hinted at rotation. The pieces began to align. Geminga was spinning, it was emitting high-energy radiation, and it had no visible companion. It fit the profile of a pulsar, but a new kind, one that didn't rely on radio waves to be seen. This wasn't just a radio-quiet pulsar, it was arguably a radio-invisible pulsar, blazing silently in the highest energies while hiding from the instruments that had found all its relatives. Jaminga's outlier status had implications far beyond its own mystery. If it was a pulsar without a radio signature, how many others might be out there, quietly blinking in gamma rays, hidden from our view simply because we weren't looking in the right way? Could our catalog of neutron stars be missing an entire population? And if so, how would that reshape our understanding of supernova remnants, neutron star formation, and the distribution of matter in the galaxy? Even as these questions took hold, Jaminga's silence persisted. Despite attempts to detect it in radio using increasingly sensitive equipment, the signals remained absent. There were occasional hints, some data that suggested perhaps a whisper of a radio pulse, but nothing definitive. And so, Jaminga retained its place as an oddity, a pulsar that seemed to communicate in gamma and X-ray only, refusing to conform to the norms. The significance of this cannot be overstated. Jaminga didn't just represent a new kind of pulsar, it represented a flaw in our methodology, a gap in our assumptions. It showed that the universe has many voices, not all of which we are prepared to hear. It forced the astronomical community to think beyond the traditional boundaries of pulsar detection and explore new ways of identifying these elusive objects. What began as an anonymous gamma-ray signal grew into a symbol of scientific humility, a reminder that even in the vastness of space, silence can speak volumes. And Jaminga was speaking, not in the expected language, but in one we were only beginning to learn how to understand. A beacon in the dark that chose a different voice, a different frequency, a reminder that the cosmos is full of secrets, and not all of them shout. The tale of Geminga's discovery begins high above the Earth's atmosphere in the early 1970s, a time when the exploration of the cosmos was entering a new phase. Up until that point, much of astronomy had relied on visible light or radio waves to decode the universe's messages. But with the development of space-based observatories, scientists began to see the cosmos in an entirely different light, literally. Among the pioneers of this shift was NASA's Small Astronomy Satellite 2, or SAS-2, launched in 1972. It was a quiet revolution. This modest satellite, no larger than a compact car, would soon detect one of the strangest and most enduring mysteries in high-energy astrophysics. SAS-2 was built for a very specific purpose: to explore the gamma-ray sky. Gamma rays, being the most energetic form of electromagnetic radiation, are incredibly difficult to detect from Earth's surface. Our atmosphere fortunately protects us from them, but this also means ground-based telescopes are blind to gamma-ray sources in space. So SAS-2 was placed in low Earth orbit to scan the sky above the atmosphere, free of interference, and ready to catch these elusive high-energy photons. Gamma-ray astronomy was still in its infancy at the time. Very few sources had been catalogued. Scientists expected to see the galactic center, perhaps a few energetic supernova remnants, and of course, bursts of gamma rays from cosmic explosions. What they did not expect was a persistent gamma-ray beacon coming from the direction of the constellation Gemini, a seemingly unremarkable part of the sky invisible, or radio light. Yet that is exactly what SAS-2 recorded. During its brief operational period, only about 6 months before the satellite's attitude control system failed, it picked up a mysterious and unusually bright gamma-ray source near the galactic plane. This source had no known counterpart. It wasn't aligned with a known supernova remnant, star, or previously identified pulsar. There was no visible object where the gamma rays seemed to originate. It simply glowed in the most energetic part of the spectrum, defying easy classification. At first, the source was referred to by its catalog designation, 2CG195+04. It was just one of several gamma-ray anomalies SAS-2 detected, but it quickly rose to prominence due to its brightness and location. This wasn't a transient burst or flare. It was a steady source of high-energy photons, persistent, structured, and strangely isolated from any known objects in lower-energy bands. The detection was significant, but puzzling. SAS-2 didn't have the angular resolution to pinpoint the source's exact coordinates with high precision. Its observations suggested that something extremely energetic was lurking in Gemini, but what exactly that was remained elusive. The gamma rays told only part of the story, and without supporting data in other wavelengths, the object's identity would remain a matter of speculation for years. In the decades that followed, this enigmatic source, later nicknamed Jaminga, continued to appear in every gamma-ray survey that came after SAS-2. When NASA launched its cosmic gamma-ray experiment on board the orbiting Solar Observatory 3, and later, the COSPI satellite by the European Space Agency, the same source glowed steadily. It was confirmed, this was no fluke, no one-time event. It was a genuine celestial object, persistent and powerful in gamma rays alone. The naming of Jaminga came later, but the mystery had already taken root. Here was a cosmic object that did not behave like the others. It had no radio signal, no optical counterpart, no easily identifiable origin. It glowed in gamma rays alone, unlike the vast majority of pulsars, quasars, or even black holes, which usually have multi-wavelength emissions. This presented a critical challenge for astronomers. Because gamma rays are so difficult to focus and trace, the lack of a corresponding optical or radio signature meant that its precise position in the sky was uncertain. Without a pinpoint location, astronomers couldn't direct other telescopes, X-ray, optical, infrared, to investigate it properly. It was like hearing a voice echoing through the night but being unable to locate the speaker. The voice kept speaking, but the figure remained in shadow. Despite these challenges, SAS-2 had done something monumental. It opened a crack in the door to an entirely new class of celestial object. The discovery of this gamma-ray-only source raised deep questions. What could emit so powerfully in gamma rays and yet be silent in other bands? Was it a neutron star behaving in a novel way? Was it something entirely unknown to science? The absence of a radio signal was particularly vexing. After all, nearly every pulsar discovered up until that point had first been identified through radio astronomy. Could this mean our understanding of pulsars was incomplete? Was this source part of a hidden population we had simply overlooked? Over the years, the significance of that initial detection grew. As more advanced instruments arrived, such as the Compton Gamma Ray Observatory in the 1990s and later the Fermi Gamma Ray Space Telescope, Jaminga was revisited again and again. But it all started with SAS-2, a humble satellite that operated for just half a year, yet managed to change the landscape of high-energy astrophysics. Its detection of 2 CG195+04 would go on to become one of the most famous unidentified sources in the entire electromagnetic spectrum. In a poetic sense, SAS-2 didn't just discover Jaminga. It initiated a mystery that would persist for generations. It asked a question that astronomy hadn't yet considered: what if a pulsar could shine without a voice? What if it could blink in gamma light but remain completely invisible to our traditional instruments? That idea, so strange and so outside the expectations of the time, was born in that moment when SAS-2 recorded something that shouldn't have existed, yet clearly did. The gamma-ray sky is a difficult terrain to explore. It doesn't offer the comfort of stars or galaxies. It speaks in bursts, in flares, in shadows of titanic energies. And among that searing landscape of light, SAS-2 found a silent outlier, a compact, persistent source of power with no face and no voice. A whisper from the void. A challenge to everything we thought we knew. That whisper would echo for decades. And Jaminga, that ghost of the gamma-ray sky, would only grow more mysterious with time. In the years that followed SAS-2's initial discovery of the enigmatic gamma-ray source in Gemini, the astronomical community found itself ensnared in one of the most perplexing identity crises in the history of astrophysics. For something so consistently bright in the most energetic wavelengths, Jaminga was frustratingly elusive in all others. No matter how carefully astronomers searched with radio, optical, and even X-ray telescopes, the object refused to reveal its full nature. It became a phantom in the sky, always present in gamma rays, but absent in every conventional sense. Throughout the 1970s and 1980s, the gamma-ray emissions attributed to the source, now increasingly referred to informally as Jaminga, remained stable. Repeated observations by successive missions like COSB only deepened the mystery. The gamma-ray light curve suggested periodicity, something that might be caused by rotation. But the angular resolution of gamma-ray detectors at the time was poor, especially compared to optical and radio instruments. The inability to pinpoint the source's exact location was a constant obstacle. This lack of spatial precision made multi-wavelength follow up a game of celestial guesswork. There could be dozens, even hundreds, of possible candidates in the error box surrounding Jaminga's suspected coordinates. The biggest challenge lay in the fundamental tools of astrophysics. Most neutron stars were identified first in radio wavelengths, and their positions refined to an astonishing degree. Those positions could then be used to find optical or X-ray counterparts. But Jaminga did not play by these rules. The traditional "follow the radio pulses" strategy failed completely, and without that anchor, researchers found themselves navigating without a compass. Some began to speculate whether Jaminga might not be a pulsar at all. Was it a quasar? A distant galaxy? A black hole with an accretion disk? Could it be a previously unknown type of astronomical object? Or even a completely new class of gamma-ray source? Over the years, increasingly sensitive radio surveys were aimed at the region, including work by large observatories like Arecibo and Green Bank. Time and again, the result was the same: nothing. No periodic radio pulses, no bursts, no steady signal. If there was a radio source associated with Jaminga, it was too weak to detect or too narrowly beamed to intersect Earth. Or perhaps it simply wasn't there at all. The lack of an optical counterpart was just as maddening. Ground-based telescopes were employed to scan the region. While stars and galaxies populated the field, none showed behavior that could be convincingly tied to a gamma-ray pulsar. And again, without a precise coordinate, astronomers were essentially looking for a needle in a cosmic haystack without even knowing which pile of hay to search in. One of the more tantalizing clues came in the late 1980s, when X-ray observatories like the Einstein Observatory and Exosat began to observe faint X-ray sources near the suspected location of Jaminga. One of these seemed particularly promising. It was soft in X-ray emission and lacked an optical counterpart. It was faint but steady. More importantly, it was located within the gamma-ray error box. A few astronomers speculated that this might be the long-sought neutron star responsible for the Jaminga signal, but without pulsations, it was still speculative. The turning point came with the launch of Rosat in 1990. This powerful X-ray satellite had far better resolution and sensitivity than its predecessors. Rosat performed a deep scan of the region and found a soft X-ray source with an interesting feature: it appeared to pulse. Specifically, it exhibited a periodicity of about 237 milliseconds. The signal wasn't easy to detect, but it was consistent, and it matched the sort of rotation one might expect from an isolated neutron star. Even more tantalizing was that this X-ray pulsation seemed to correlate with a gamma-ray signal that had been tentatively seen in the COSPI data, though that data was too noisy to confirm. This raised the possibility that Jaminga was, in fact, a pulsar, one that simply did not emit in radio wavelengths, or whose radio beam missed Earth entirely. The Rosat detection was enough to reinvigorate the community's interest, and now that a candidate had been found in X-rays, the door was open for optical follow-up. In 1993, the final proof came from timing observations using NASA's EGRET instrument aboard the Compton Gamma Ray Observatory. EGRET detected pulsations in gamma rays that matched the X-ray period found by Rosat exactly, 237 milliseconds. This was the smoking gun. There could be no mistake now: Jaminga was a pulsar. Not just any pulsar, but the first to be identified primarily through its gamma-ray emission. The conclusion was astonishing. For 20 years, astronomers had been staring at a neutron star that hid its presence in every wavelength but the most energetic. But even after this revelation, questions remained. Why didn't Jaminga emit in radio? Was it just a matter of beaming geometry, its radio beam pointing away from Earth? Was it a truly radio-quiet pulsar, an entirely new class of object? Or was there some unknown mechanism that suppressed or absorbed its radio emission? This period of discovery, spanning nearly 2 decades from SAS-2's initial detection to EGRET's pulsation confirmation, stands as a testament to the difficulty of multi-wavelength astronomy and the patience of the scientific process. It also highlights the limitations of relying too heavily on a single method of observation. If SAS-2 hadn't been launched, if gamma-ray astronomy hadn't advanced, Jaminga might have remained just another unexplained dot in the sky, misunderstood, misclassified, or even ignored. As it stands, those decades of uncertainty now read like a slow-burning detective novel. Each chapter brought new characters, new observatories, new theories, new hypotheses. Each instrument revealed a new layer of the puzzle. From SAS-2's first detection, to COSBS follow-up, to Rosat's breakthrough, to EGRET's decisive confirmation, the search for Jaminga's identity became a multi-generational quest. And even once that quest was seemingly resolved, once the label, pulsar, was finally affixed to it, the deeper mystery remained. For all its revealed identity, Jaminga still refused to speak in the language that all others of its kind used so freely. It was, and remains, a silent sentinel, more visible than ever, yet just as enigmatic as the day it was first seen. The breakthrough that would finally transform Jaminga from a nameless gamma-ray phantom into a confirmed neutron star began with the German-led Rosat mission, short for the Röntgen satellite, launched in 1990. This X-ray observatory was a technological leap forward in soft X-ray astronomy. Where earlier missions had provided rough detections and hazy images, Rosat brought unprecedented clarity. Its sensitivity and spatial resolution were precisely what astronomers needed to finally pierce through the fog that had surrounded Jaminga for nearly 2 decades. At the time, Jaminga's position was known only to within a few degrees. That's a vast area in astronomical terms, enough to contain thousands of background stars, galaxies, and noise sources. The COSB satellite in the 1980s had slightly narrowed the error box of the gamma-ray signal, but the region was still too large for efficient cross-referencing with radio or optical surveys. That's where Rosat stepped in, equipped with the ability to scan that wide area and identify X-ray sources with arc-minute precision. It was, metaphorically, like swapping a foggy pair of glasses for a pair of binoculars. When Rosat focused on the region of the sky identified by COSB, it found several X-ray sources, but one stood out. This source didn't have a known optical counterpart. It didn't appear to vary wildly over time like a black hole binary might. It wasn't associated with a galaxy or a cluster. And it had a soft X-ray spectrum, characteristic of thermal radiation, the kind that could come from the surface of a hot neutron star cooling over time. That alone made it an excellent candidate for the long-sought counterpart to Jaminga's persistent gamma-ray glow. But it was what came next that electrified the astrophysical community. Rosat's high-resolution imager, HRI, revealed that this source wasn't just static, it was pulsing. Very faintly, but undeniably, the object exhibited a periodic modulation in X-ray brightness at an interval of about 237 milliseconds. A blink, nearly a quarter of a second long, repeating over and over again. To the trained eye of an astrophysicist, that periodicity was a dead giveaway. They were likely looking at the rotation of a neutron star, one of nature's most compact and extreme creations. A rotation rate of 4 times per second was consistent with what one would expect from a middle-aged pulsar, not a newborn spinning hundreds of times per second, but not yet slowed down into obscurity either. Still, caution was needed. Periodic signals can sometimes be artifacts, tricks of data sampling or statistical noise. Confirmation had to come from other sources. Yet Rosat had done what no telescope had managed to do since SAS-2's discovery in 1972. It had provided a precise location and a possible timing signature. The veil was finally lifting. Once Rosat provided coordinates with arc-second accuracy, optical astronomers joined the fray. Deep images of the region were taken in visible and ultraviolet light. What they found was astonishingly faint, an object barely above detection limits. This potential optical counterpart had no features typical of stars or galaxies. Its color and lack of variability pointed toward a cooling neutron star, emitting only the residual thermal radiation left over from its violent birth in a supernova explosion hundreds of thousands of years ago. The optical signature, though weak, was consistent with a surface temperature of around 1,000,000 degrees Kelvin, precisely what one might expect from a middle-aged neutron star. And the nail in the coffin, the final confirmation, came soon after. NASA's Compton Gamma Ray Observatory, which had launched in 1991, carried on board the EGRET instrument, one of the most advanced gamma-ray detectors of its time. EGRET was sensitive enough to measure gamma-ray pulses, something COSB had been too weak to do. Using the precise period and coordinates provided by Rosat, scientists went back through EGRET's data and found it, matching pulsations at exactly 237 milliseconds in gamma rays. The odds of that being a coincidence were effectively zero. It was conclusive. The gamma-ray source discovered by SAS-2 in 1972, identified as Jaminga, was indeed a neutron star, a pulsar, rotating every 237 milliseconds, emitting beams of gamma rays and X-rays but mysteriously quiet in the radio band. A pulsar that had, for 2 decades, defied every standard detection method and eluded classification, was finally unmasked. The significance of the Rosat breakthrough cannot be overstated. It rewrote the rulebook for how astronomers could identify pulsars. Until then, nearly all known pulsars were found by their radio pulses, often by accident during surveys. Rosat had helped prove that a neutron star could be discovered through its X-ray and gamma-ray emissions alone, inaugurating a new category, the radio-quiet pulsars. Furthermore, the discovery added credibility to the idea that the pulsar population in the galaxy was larger and more diverse than previously imagined. How many other Jaminga-like objects, silent in radio but blazing in high energies, might be lurking undetected in our galaxy? How many had been passed over simply because we were looking with the wrong eyes? With Rosat's data, Jaminga had become more than just a mystery, it had become a watershed. Its success showcased the power of multi-wavelength astronomy, how combining data from multiple parts of the electromagnetic spectrum can yield truths that no single band can reveal alone. Gamma rays alone had pointed the way. X-rays had revealed the pulse. And gamma rays, in turn, had confirmed the identity. It was a perfect loop, an orchestration of instruments, an insight that brought the invisible into focus. Even after the confirmation, Jaminga retained its air of mystery. For one, its radio silence remained unresolved. Theories began to swirl. Perhaps its radio beams simply didn't intersect Earth. Or maybe its radio emission was too faint to detect with current technology. Some even suggested that Jaminga might emit radio waves intermittently, or at very low frequencies we hadn't yet scanned with enough sensitivity. Others proposed absorption of radio signals by the interstellar medium, though the line of sight didn't support dense clouds. Still, the breakthrough had been made. For the first time, a pulsar had been positively identified not by what it said in the radio, but by how it whispered in X-rays and shouted in gamma rays. And that moment, powered by the precision and persistence of the Rosat Observatory, marked a turning point in high-energy astrophysics. The once nameless, voiceless ghost in Gemini now had coordinates, a rotation period, a cooling surface, and a proper classification. Jaminga had stepped out of the shadows, though its silence still echoed as loudly as its newfound brilliance. With the pulsations in both X-rays and gamma rays now confirmed, the path to establishing Jaminga's identity as a neutron star, specifically a pulsar, was finally wide open. But confirmation in science doesn't come with a single, eureka, moment. It's a convergence of evidence across different domains, each piece reinforcing the next until the conclusion becomes unassailable. In Jaminga's case, what followed the Rosat and Egret discoveries was a rapid-fire sequence of observations and theoretical work that brought a once mysterious gamma-ray source into the fold of well-understood, though still strange, neutron star behavior. To begin with, the detection of pulsations, at exactly 237 milliseconds in both X-ray and gamma-ray bands, was the defining feature that signaled a rotating object. But not just any rotating object. The period was too fast for a planet, too fast for a white dwarf, and too stable to be an artificial signal or background noise. Only neutron stars spin that quickly while maintaining coherence over extended periods of time. Neutron stars, the dense remnants of supernova explosions, can preserve rotational speeds of several times per second, their angular momentum conserved from the collapsing core of a massive progenitor star. And Jaminga, with its 237 millisecond spin, was squarely within the expected range for a middle-aged pulsar. Additional evidence came from how those pulsations were modulated. In both the X-ray and gamma-ray domains, the pulses showed broad, double-peak structures, something seen in many known pulsars. This pulse profile hinted at the shape of the emission regions and the geometry of the star's magnetic field. The energy dependence of these pulses, how their brightness and timing shifted slightly between X-ray and gamma-ray bands, offered clues about where and how the radiation was being emitted. For Jaminga, the patterns suggested that its high-energy emissions were being produced in the outer magnetosphere, far from the surface, in a region where intense electric fields accelerated particles to near-light speeds. This again was textbook pulsar behavior, minus the radio. Next, astronomers looked to the timing behavior. A hallmark of pulsars is that their spin slows down over time, as energy is lost to radiation and particle winds. With Jaminga's newly established pulse period, astronomers could now monitor its rotation rate with great precision. They observed what's known as a spin down, a tiny but measurable increase in its period over years. This deceleration rate, or period derivative, can be used to infer several properties: the pulsar's magnetic field strength, its age, and its total rotational energy loss, the so-called spin-down luminosity. Jaminga's spin-down rate was consistent with a relatively middle-aged pulsar, approximately 300,000 years old. Its inferred magnetic field was about 1.6 x 10 superscript 1 superscript 2 Gauss, strong enough to power gamma-ray emission, but not as intense as younger, more violent pulsars like the crab. This magnetic field strength was in perfect harmony with the kind expected for a classical rotation-powered pulsar. It also explained why the pulsar was still energetic enough to shine in high-energy wavelengths despite its advancing age. Meanwhile, another piece of supporting evidence emerged from Jaminga's motion through space. Using Rosat's highly accurate astrometry and follow-up optical imaging, astronomers detected proper motion, a subtle shift in the position of the object over time. This movement through the sky suggested that Jaminga was relatively close to Earth, about 800 light-years away, and moving at high speed, estimated at over 200 kilometers per second. This kind of proper motion is characteristic of neutron stars, which are often kicked during the violent supernova events that birth them, sending them hurtling through the galaxy like cosmic bullets. Its apparent proximity also helped explain why Jaminga was so bright in gamma rays yet invisible in radio. Gamma rays are less affected by interstellar absorption and can travel great distances unimpeded. But if the object was close and relatively cool, its radio beam might simply be misaligned with Earth, or be intrinsically weak, making detection difficult with standard methods. This idea strengthened the argument that Jaminga might represent a broader class of nearby neutron stars that are missing from the radio catalogs not because they don't exist, but because our instruments are not aligned to receive their signals. In parallel with these observational campaigns, theoretical work was flourishing. Astrophysicists began building models specifically for Jaminga to account for its unusual emission profile. Outer gap models of pulsar magnetospheres were refined to explain its gamma-ray production, particularly the observed phase offset between X-ray and gamma-ray pulses. These models predicted that particles in the upper magnetosphere, curving along magnetic field lines, could emit curvature radiation in the gamma-ray band, while lower-energy particles near the star's surface emitted thermal X-rays. The details of these models matched Jaminga's observed light curves with surprising accuracy. Another avenue of confirmation came from studying Jaminga's X-ray spectrum. Rosat and later XMM Newton data showed that the emission wasn't uniform. It had both a thermal component and a non-thermal component. The thermal part, emitted by the hot surface of the neutron star, peaked in the soft X-ray band and was best fit by a blackbody spectrum at roughly 500,000 to 1 million Kelvin. The non-thermal part extended into higher energies and was consistent with synchrotron or curvature radiation, matching the behavior expected from charged particles spiraling through intense magnetic fields. This hybrid X-ray spectrum further cemented Jaminga's classification as a neutron star. No other known objects had quite this blend of emission properties. Not black holes, not white dwarfs, not even active galactic nuclei. Only neutron stars offered a satisfactory fit to all the data across multiple wavelengths. And so, with pulse timing, spin down, proper motion, emission spectra, and theoretical modeling all aligning, the scientific community could finally close the case. Jaminga was not just a neutron star, it was a pulsar. A high-energy, radio-quiet, middle-aged pulsar about 800 light-years from Earth, spinning 4 times per second, lighting up the sky in X-rays and gamma rays, and whispering secrets of extreme physics from the edge of visibility. But this conclusion didn't end the mystery, it only sharpened it. Because now that Jaminga had been confirmed as a neutron star, the question became, why does it refuse to emit radio waves like the others? Or worse, what if it does emit them, but we simply haven't been clever enough to detect them? What does Jaminga's silence say about the broader population of neutron stars out there, and how many more might be hiding in plain sight? The identification of Jaminga as a neutron star, a pulsar, should have brought a sense of closure. After all, pulsars were originally discovered as radio sources. Radio astronomy had been the primary tool for cataloging hundreds of these celestial clocks. Yet with Jaminga, something fundamental was missing: the radio pulses. Even as astronomers basked in the triumph of finally confirming its identity through X-rays and gamma rays, the lingering absence of radio emission presented a new, equally perplexing challenge. It was like discovering a lighthouse that beamed in ultraviolet and infrared but cast no light in visible wavelengths, an oddity that refused to conform. The problem wasn't that Jaminga was undetectable. On the contrary, it was one of the brightest persistent sources in the gamma-ray sky. Its X-ray signature, though more modest, was steady and periodic. Yet all attempts to detect it in the radio, where most pulsars announced themselves, ended in failure. Repeated surveys, some targeting known pulsar frequencies, others scanning more broadly, yielded nothing. The usual burst of pulses, that rhythmic ticking which gave pulsars their name, was absent. Jaminga was completely mute in the domain where its cousins chattered constantly. To grasp how unusual this was, consider that radio emissions are the defining feature of most pulsars. The classic model of a pulsar describes a neutron star with a powerful magnetic field misaligned with its spin axis. As it rotates, beams of radiation shoot out from its magnetic poles, and if Earth lies in the path of these beams, we see periodic pulses, most often in radio wavelengths. From these pulses, astronomers can derive rotation rates, infer magnetic field strengths, and even use them as galactic clocks. So when a neutron star like Jaminga spins with clockwork regularity and shines brilliantly in gamma rays, but shows no radio pulses, it forces us to re-examine everything we thought we knew about how pulsars work. Why would a neutron star emit in X-rays and gamma rays, but not radio? The most straightforward explanation, and the one most favored by theorists, is one of geometry. The pulsar model hinges on where the beams point. If the radio beam is narrow and directed away from Earth, we never detect it, even though it's there. Imagine a lighthouse whose light circles just above your line of sight. You might see its glow in the sky, feel its influence on other objects, but never catch the beam directly. In this view, Jaminga is not truly radio silent, it's simply radio invisible to us. This geometry hypothesis makes a lot of sense when we consider how beams are structured across different wavelengths. High-energy emissions like gamma rays often originate higher in the magnetosphere, where the magnetic field lines flare outward. These beams are generally broader and less sharply confined than radio beams, which are thought to arise closer to the magnetic poles. A pulsar's gamma-ray beam might sweep over Earth while its radio beam misses us completely. Still, this explanation, though elegant, raises further questions. If geometry is the only issue, why haven't we seen even weak or scattered radio signals from Jaminga? Other pulsars with similar profiles often show faint or sporadic radio bursts, signals that are detectable with sufficiently sensitive instruments. Yet even deep observations with large radio telescopes, including Arecibo, the Very Large Array, and Parkes, failed to find consistent pulses from Jaminga. This stubborn silence suggests that something more may be at play. Could the radio emission be intrinsically weak? Perhaps Jaminga's magnetic field or plasma environment doesn't support strong radio production. Or maybe it once emitted radio waves but now, after hundreds of thousands of years, the conditions in its magnetosphere have changed, cooling, decay, or a realignment that turned the radio beam off. While the gamma-ray and X-ray emissions are powered by relativistic particles in the outer magnetosphere, radio emission is believed to be tied to coherent processes near the star's surface. If those conditions aren't met, due to magnetic field decay, particle scarcity, or plasma suppression, radio waves might simply not be generated at all. An even more provocative theory considers interstellar absorption. Could intervening clouds of ionized gas or magnetic fields be scrambling or blocking the radio waves before they reach us? It's an enticing idea, but one that doesn't quite hold up under scrutiny. The line of sight between Earth and Jaminga does pass through interstellar material, but not an unusual amount. For a pulsar only 800 light-years away, the interstellar medium is relatively sparse. Radio waves should, in theory, pass through such space with little attenuation, especially at the lower frequencies that pulsar surveys typically use. Absorption can't fully account for the complete lack of signal. Then there's the tantalizing possibility that we have seen Jaminga's radio signal, just barely. Some researchers have reported marginal detections at low frequencies, particularly around 100 MHz. In the late 1990s and early 2000s, several studies claimed to have picked up weak, intermittent radio pulses that seemed to match Jaminga's rotation period. These detections, however, were at the edge of statistical significance and have not been universally confirmed. Other observations failed to replicate the findings, leading to debates about whether the signals were real or artifacts. If those faint radio signals are real, it would suggest that Jaminga isn't completely silent, just incredibly quiet. A whisper of radio sound amid the roar of gamma rays. Such a scenario would lend credence to models suggesting that Jaminga is barely clinging to its radio-producing capabilities, perhaps at the end stage of its radio-loud life. This would position it as a transitional object, a pulsar evolving from a bright radio phase to one dominated by high-energy emissions. If true, that would make Jaminga a unique laboratory for studying the life cycles of pulsars and the dynamics of their magnetospheres over cosmic time. Another idea that's emerged in recent years is that the mechanisms responsible for radio and gamma-ray emissions are more decoupled than previously thought. Instead of originating from different heights in the same magnetic structure, they might arise from distinct processes altogether. Some theorists have proposed that certain neutron stars might enter a state where coherent radio emission fails completely, while incoherent gamma-ray and X-ray emission continues unabated. In this model, Jaminga is not a one-off curiosity but part of a broader, and undersampled, population of radio-dead, or radio-deficient, pulsars. This notion has gained traction with the discovery of more gamma-ray-only pulsars by the Fermi Gamma-Ray Space Telescope. Since its launch in 2008, Fermi has uncovered dozens of pulsars that, like Jaminga, shine brightly in gamma rays but emit no detectable radio waves. Many of these are now classified as radio-quiet or radio-invisible pulsars, and they reinforce the idea that Jaminga is not an anomaly but the prototype of a much larger class of neutron stars. So, where is Jaminga's radio voice? It may be whispering faintly, too softly for us to hear. It may be pointing in the wrong direction, casting its signals into a void we'll never cross. Or it may have gone silent entirely, its radio beam extinguished by time, physics, or fate. Whatever the cause, the silence is profound, not just because it defies expectations, but because it speaks volumes about the limits of our understanding. In the end, the absence of radio pulses is not a gap in data. It is itself a form of data. A puzzle piece that doesn't fit the existing model compels us to redraw the edges of the picture. And in the case of Jaminga, the silence is not empty. It is resonant. It forces us to confront the possibility that the universe is far more diverse in its manifestations than we dared to imagine. That some lighthouses shine in ultraviolet, others in X-ray, and some, in the case of Jaminga, beam with the invisible, scorching light of gamma rays alone. While traditional pulsars introduce themselves to the cosmos through the regular, ticking rhythm of radio waves, a new breed of neutron stars has emerged. Ones that defy this auditory expectation and instead blaze in the silence of high-energy light. These are the gamma-ray pulsars, and Jaminga is their enigmatic poster child. To understand what makes them so fascinating, we must first delve into the physics that allows some pulsars to emit almost exclusively in gamma rays and X-rays, bypassing the radio spectrum entirely or reducing it to a whisper. Gamma-ray pulsars still operate under the same fundamental principles as all pulsars, a rapidly spinning neutron star with an intense magnetic field, often exceeding 1 trillion times Earth's own, and a rotation rate that can reach hundreds of revolutions per second. This immense energy, born in the aftermath of a supernova, drives the pulsar's entire light show. But the key difference in gamma-ray pulsars lies in where and how that energy is released. In the classical model, pulsar radiation is believed to arise from regions near the magnetic poles, where charged particles, primarily electrons and positrons, spiral along curved magnetic field lines, generating beams of radiation. For many pulsars, this emission appears strongest in radio wavelengths. However, high-energy pulsars like Jaminga behave differently. Their gamma-ray and X-ray emissions originate much further out in the magnetosphere, the area dominated by the pulsar's magnetic field. Here, the physics changes. Instead of slow, dense plasma near the neutron star's surface producing radio waves through coherent mechanisms, the outer magnetosphere becomes a chaotic accelerator for individual particles, creating incoherent, high-energy bursts. One of the most well-supported models to describe this is the outer gap model. In this framework, gaps in the pulsar's magnetosphere, areas where electric fields are not fully neutralized by surrounding particles, act as particle accelerators. Electrons and positrons are hurled through these gaps at nearly the speed of light, slamming into photons and magnetic fields, and releasing powerful gamma rays in the process. These emissions are directional, spread out in sweeping cones that can span a large portion of the sky. It's this broader beam width that allows Earth to catch glimpses of gamma-ray pulsars like Jaminga, even if we're outside the line of sight for their narrower radio emissions. Another popular framework is the slot gap model, which proposes that high-energy radiation arises in narrow, elongated gaps that trace the last open magnetic field lines near the polar caps. These field lines stretch out to the light cylinder, the imaginary cylinder where the co-rotation speed of the magnetic field would match the speed of light. The slot gap is a particularly fertile environment for gamma-ray production because of its strong accelerating fields and rapid particle motion. In this model, gamma-ray emission is again generated via curvature radiation, inverse Compton scattering, and synchrotron processes, with the gamma rays beaming outward in a fan-like spray. The emissions cover a wide swath of sky and can easily encompass Earth's line of sight even if the radio beams do not. Importantly, these high-energy beams do not blink on and off like the pulses of a flashlight. Instead, they're shaped by the structure of the pulsar's magnetic field and the rotation of the neutron star. The result is periodicity, just like radio pulsars, but in far more energetic wavelengths. For astronomers using telescopes like NASA's Fermi Gamma-Ray Space Telescope, this means they can still detect the spin of the pulsar, even without a single radio photon. By timing the arrival of gamma-ray photons and matching them to known periodic patterns, researchers can reconstruct the pulsar's spin, rotation decay, and even glitches, sudden changes in rotation speed. But why would some pulsars emit almost entirely in gamma rays? One factor is age. Jaminga is estimated to be around 300,000 years old, not ancient in cosmic terms, but old enough that its energy output has evolved. Younger pulsars tend to be more prolific radio emitters, with stronger magnetic fields close to their surfaces. As a pulsar ages, its magnetic field decays and the conditions needed for coherent radio emission may no longer exist. However, its rotation can still power outer magnetospheric acceleration and the production of gamma rays. In this sense, gamma-ray pulsars might represent an evolutionary stage, older neutron stars that have transitioned out of their radio-bright youth into a quieter but still dazzling maturity. Another contributing factor is alignment. The orientation of the pulsar's magnetic axis relative to its spin axis, and both of those relative to Earth, can drastically influence what emissions we see. Gamma-ray beams are typically broader and originate further from the neutron star, meaning they're more likely to intersect Earth's line of sight even if the radio beams, which are tighter and emitted closer to the poles, miss us completely. Thus, many radio-quiet pulsars might not be silent at all, they're just whispering in directions we can't hear. Recent studies using Fermi and other observatories have uncovered dozens of gamma-ray pulsars that follow this pattern. Some have extremely weak or non-existent radio signals. Others produce intermittent bursts or flashes, possibly from rare alignments or magnetospheric instabilities. Jaminga fits neatly into this category, a brilliant gamma-ray source, with a clear and consistent spin signature, but a ghost in the radio band. It's not alone, but it was among the first to alert astronomers that the pulsar population was far more diverse than anyone had imagined. There's also the matter of emission efficiency. Gamma-ray pulsars like Jaminga are often incredibly efficient at converting their rotational energy into gamma-ray photons. Some models suggest that upwards of 20 to 30% of their spin-down energy, the energy lost due to slowing rotation, is channeled directly into gamma-ray emission. By contrast, radio emission accounts for a tiny fraction of a pulsar's energy output, often far less than 1%. In other words, gamma-ray emission is not just more energetic, it's also a more dominant part of a pulsar's life at certain stages. Even the environment around the pulsar plays a role. A dense or magnetically turbulent region could suppress certain wavelengths while enhancing others. Magnetic reconnection events, plasma turbulence, and surface instabilities may all shape the final emission profile. In such conditions, radio production might be extinguished while high-energy processes are enhanced. Gamma-ray pulsars like Geminga have another trait in common. They often travel at incredible speeds. Jaminga, for example, is zipping through the galaxy at several hundred kilometers per second. This motion creates bow shocks in the interstellar medium and trailing winds of energetic particles, processes that can interact with and sometimes amplify high-energy emissions. These tails and halos, seen in X-ray and gamma-ray observations, may further boost the visibility of such pulsars in the high-energy sky. What Jaminga and its kind ultimately teach us is that the universe is not constrained by our instruments. For decades, astronomers believed pulsars were primarily radio objects, simply because that's how they were first seen. But gamma-ray pulsars have exposed the observational bias in that assumption. They remind us that the cosmos operates across an electromagnetic spectrum far broader than human eyes, or even our early telescopes, could see. By broadening our search methods and embracing new detection techniques, we've uncovered a hidden universe of high-energy pulsars. And Jaminga, once a riddle wrapped in a gamma-ray glow, now serves as a guidepost in this expanding realm. It is not a deviation from the rule, but a revelation of just how incomplete our rulebook really was. As we continue to listen across the spectrum, from low-frequency radio to the highest energy gamma rays, we will no doubt find many more stars that, like Jaminga, sing their stories not in sound, but in fire. One of the most compelling explanations for Jaminga's silence in the radio spectrum is known as the beaming geometry hypothesis. This idea hinges on a simple but profound realization: we don't see what isn't pointed at us. When we observe a pulsar, we're essentially catching its lighthouse beam as it sweeps past our line of sight. If that beam never crosses Earth's position, then the pulsar, no matter how loud it may be in the radio spectrum, will appear utterly silent to us. This may very well be the case for Jaminga. Pulsars emit radiation from regions near their magnetic poles, but those magnetic poles are typically misaligned with the neutron star's axis of rotation. This creates a sweeping effect, as if the star is waving two flashlights in a slow circle. For some pulsars, both beams are visible from Earth. For others, only one is. And for a select few, either beam intersects our planet's line of sight. If that's the case, we won't detect any pulsations at all in the radio band. In Jaminga's case, gamma rays and X-rays are a different story. High-energy emissions originate from more extended regions of the magnetosphere, often from much higher altitudes above the star's magnetic poles. These outer regions are not only more energetic but also geometrically broader, casting their radiation over a larger section of the sky. That's why we can still detect the gamma-ray pulses from Jaminga even if we never cross paths with its narrow radio beams. This brings us to the critical role of geometry. The beaming geometry of a pulsar is defined by two key angles: the inclination angle, which is the tilt between the rotation axis and the magnetic axis, and the viewing angle, which is the angle between the rotation axis and the observer's line of sight, in this case, us on Earth. If these angles align in just the right, or wrong, way, we may completely miss the radio beam while still catching the broad swath of gamma-ray emissions. Extensive modeling of Jaminga's emission patterns has supported this idea. By comparing the light curves, graphs of intensity versus time, of Jaminga's gamma-ray pulses with theoretical models of emission geometry, astronomers have been able to infer plausible ranges for the inclination angle and the viewing angle. Many of these models suggest that the radio beams are simply not sweeping across Earth, while the high-altitude gamma-ray emissions are. It's as if Jaminga is turning its head just slightly to the side, looking past us rather than at us. One of the tools scientists use to explore these geometries is polarization. In radio pulsars, the polarization of the signal provides critical information about the orientation of the magnetic field and the path of the beam. But for Jaminga, this tool is largely unavailable because of the lack of a strong radio signal. Instead, astronomers rely on modeling, comparing Jaminga's gamma-ray light curves with those of known pulsars and running simulations based on plausible magnetic field configurations. Interestingly, there's statistical support for the beaming hypothesis beyond just Jaminga. Observations from the Fermi Gamma-Ray Space Telescope have revealed a growing population of gamma-ray pulsars that are either weak or undetectable in the radio band. If all pulsars emitted their radiation uniformly in all directions, this discrepancy wouldn't exist. But the fact that some are radio loud and others are radio quiet suggests that directionality, the geometry of the beams, plays a significant role in whether we detect them. Some models even attempt to estimate the fraction of all pulsars that might be undetected due to beam misalignment. These studies suggest that for every radio pulsar we discover, there may be several others, possibly even a majority, that are invisible to us in radio but detectable in gamma rays. If true, then Jaminga is not alone. It's part of a vast, hidden network of neutron stars whispering across the galaxy in gamma radiation, their radio voices aimed elsewhere. In addition to geometric considerations, there is another layer of complexity: beam evolution over time. As pulsars age, their emission properties can change. The radio beam might become narrower, or its axis might precess slowly due to internal instabilities or external torques. These changes could bring the beam into or out of Earth's view over thousands of years. It's possible that Jaminga was once visible as a radio pulsar and has since rotated out of alignment, or that it may become visible again in the distant future. There's also a less likely but intriguing possibility: Jaminga's magnetic axis may be aligned closely with its rotational axis. In such a case, the pulsar's beams would sweep in tight, symmetrical circles around the spin axis, essentially forming a narrow cone. If Earth happens to lie outside this cone, we wouldn't see any pulses, particularly in the radio band, which is more tightly focused than gamma-ray emission. In this scenario, the geometry alone, without any exotic physics, would be sufficient to explain Jaminga's radio silence. Adding weight to the beaming hypothesis, some astronomers have even attempted to detect Jaminga's radio pulses through innovative methods. By looking at specific times when subtle changes in its rotation or environment might momentarily alter the beam's path. A few studies have claimed extremely faint detections, but none have been robust or repeatable enough to confirm the presence of a reliable radio pulse. The majority view remains that Jaminga is effectively radio silent because its beam never points our way. The implications of the beaming geometry hypothesis are profound. It reminds us that our ability to observe the universe is shaped not just by the existence of phenomena but by our position relative to them. We are passive observers, relying on celestial objects to direct their emissions our way. In the case of Jaminga, the cosmic spotlight of radio simply passes us by, while the floodlight of gamma rays continues to bathe our detectors in brilliant bursts. This theory doesn't close the case on Jaminga's silence. It's one piece of the puzzle. But it's a powerful, elegant explanation that aligns with everything we know about pulsar physics, emission mechanics, and observational statistics. Jaminga, it turns out, might not be mute at all. It could simply be speaking fluently in radio, but to someone else, somewhere else in the galaxy. Another fascinating explanation for Jaminga's radio silence builds upon the beaming hypothesis, but adds an extra layer of specificity. This is the narrow beam model, which suggests that Jaminga does emit radio waves like other pulsars, but its radio beam is unusually thin, tightly collimated, and possibly so fine that even the smallest misalignment causes Earth to miss it completely. While the geometry hypothesis explains why any normal beam might fail to intersect our planet, the narrow beam model proposes that Jaminga's beam isn't just misaligned, it's simply too narrow to reach us, even under otherwise favorable conditions. To understand this, consider how the typical pulsar emits its energy. In most cases, radio emissions arise from regions very close to the neutron star's magnetic poles, forming conical beams that sweep through space as the pulsar rotates. The width of these cones, or beams, is usually proportional to the star's rotational period. Pulsars that spin faster tend to have wider beams, and slower ones, narrower. Jaminga's rotational period is around 237 milliseconds, which places it in a middle category, not especially fast, not especially slow. Based on statistical models, one would expect a beam wide enough to be detectable if it were pointed in our direction. But what if Jaminga's beam is abnormally thin, even for its spin rate? This would mean that even a slight offset from our line of sight would render the radio pulse invisible to us. And if this narrowness is due to some intrinsic property of the pulsar, its magnetic field configuration, surface temperature, plasma dynamics, or evolutionary stage, then it would represent a rare but plausible deviation from the standard model. One proposed mechanism for this narrow beam focuses on Jaminga's magnetic field. Pulsars don't just emit radiation, they shape it, channel it, and constrain it through intense magnetic fields that are trillions of times stronger than anything Earth-based. These fields direct the charged particles that generate radio waves along curved paths that align with the field lines. If Jaminga's field lines are particularly tightly wound or spatially confined, they may form an emission region that is much smaller than usual. This would produce a radio beam that looks more like a laser pointer than a flashlight. Another possible contributor to a narrow beam is the plasma density in Jaminga's magnetosphere, the region of charged particles surrounding the pulsar. If this plasma is denser or more turbulent than normal, it might suppress the growth of the emission cone. The beam could then appear as a thin spike rather than a full arc. This would not only explain the absence of a detectable pulse from Earth but might also imply that only a small fraction of the sky is ever illuminated by Jaminga in radio frequencies. There's also a theoretical framework that links beam width to pulsar age. As pulsars get older, their magnetic fields may decay or change structure, potentially leading to narrower emission regions. Jaminga is estimated to be about 300,000 years old, ancient by human standards, but still middle-aged for a pulsar. If this stage in its life cycle naturally leads to tighter radio beams, then Jaminga might be one of the first known examples of such behavior. In fact, some researchers suggest that many missing radio pulsars could simply be older neutron stars with increasingly narrow beams that no longer cross Earth's sideline. Support for the narrow beam model comes from statistical studies as well. When examining the known population of radio pulsars, astronomers have noted a fall-off in detections among objects with certain spin periods and magnetic field strengths. This could be an observational bias, not because such pulsars don't exist, but because their beams are too narrow to be detected. Jaminga fits right into this observational gap, hinting that it may be one of a large, hidden family of neutron stars that are simply too fine-tuned in their emissions to be picked up in radio surveys. The narrow beam idea also holds up under simulations. When computer models recreate pulsar beam shapes under various physical conditions, magnetic field intensity, surface temperature, rotation speed, they find that certain parameter combinations do indeed produce unusually thin beams. Jaminga's inferred properties, especially its intermediate spin and relatively weak surface temperature compared to younger pulsars, fall near this range. These simulations reinforce the plausibility that Jaminga's radio beam exists, but is simply too slender for our instruments to catch. It's worth noting, too, that the narrow beam model doesn't require the complete absence of a radio signal. It just means the signal is so highly directional that it misses us. In this framework, Jaminga could be blasting out radio pulses consistently, but along a microscopic celestial slit that never intersects our part of the sky. This raises an intriguing possibility. If we were located just a fraction of a light-year to one side, still within the same galactic neighborhood, we might hear it loud and clear. There have even been efforts to explore whether such a narrow beam might wobble slightly over time due to precession, a slow, gyroscopic movement of the neutron star's spin axis. If Jaminga's beam precesses over millennia, it might periodically swing into Earth's line of sight, briefly lighting up our detectors before disappearing again. So far, no such event has been observed, but the idea keeps astronomers vigilant for transient signals that could emerge in the future. The implications of the narrow beam model ripple out across astrophysics. If pulsar beams can be this narrow, then many neutron stars might be going undetected, skewing our census of the galaxy's pulsar population. It would mean our understanding of neutron star birth rates, magnetic field decay, and beam morphology needs adjusting. For every pulsar we detect, there could be dozens more whose whispers never reach us, not because they are silent, but because they're whispering sideways. Jaminga may not be unique. It could be the visible tip of an invisible iceberg, a sentinel of a deeper truth about the structure and behavior of pulsar beams. Its narrow beam silence challenges us to refine our tools, reframe our assumptions, and remain aware of the possibility that the universe is much busier and far more precise than it sometimes appears. The theory that Jaminga's radio silence might be caused not by its intrinsic properties or orientation, but by something in between, namely, the interstellar medium, adds a compelling third dimension to the mystery. Known as the absorption hypothesis, this idea suggests that Jaminga's radio signals are indeed being emitted, but are simply absorbed, scattered, or otherwise lost before they ever reach Earth. In this scenario, Jaminga's radio whisper doesn't go unheard because it isn't directed at us, but because the message is garbled before it arrives. To explore this theory, we have to journey through the intervening space between Earth and Jaminga, approximately 800 light-years of the interstellar medium, or ISM. The ISM is not a perfect vacuum. It's a complex, ever-changing soup of gas, dust, plasma, and magnetic fields. And radio waves, like any form of electromagnetic radiation, interact with this medium in several ways. They can be refracted, dispersed, scattered, or outright absorbed, depending on their frequency and the properties of the material they travel through. Lower frequency radio waves, exactly the kind emitted by pulsars, are particularly vulnerable to these effects. One of the most well-known phenomena is dispersion, in which lower frequency components of a signal are delayed more than higher frequency components as they pass through free electrons. This effect is predictable and actually useful. It helps astronomers calculate the electron density along the line of sight, yielding a dispersion measure that often aids in identifying the distance to a pulsar. But in more extreme cases, these interactions can lead to absorption or scattering so intense that the radio signal is effectively erased. The key suspects here are regions of dense plasma or clouds of cold, neutral hydrogen, particularly if they contain small dust grains or molecular clumps that absorb low-frequency radiation. If Jaminga lies behind, or within, such a region, then its radio beam could be heavily attenuated or smeared out to the point of invisibility. The idea gains some plausibility when we consider Jaminga's location in the galaxy. It's situated in the galactic plane, a region that is richer in gas and dust compared to the halo or outer disk. And though Jaminga is relatively close on a galactic scale, there's still plenty of room between here and there for complex interstellar structures to intervene. In fact, we know that certain regions of the sky exhibit anomalously high absorption in radio frequencies, and lines of sight through those regions can obscure even relatively strong sources. In support of this, some X-ray observations of Jaminga have revealed interesting features in its surrounding environment. The pulsar is known to be moving supersonically through space, producing a bow shock as it plows through the ISM. This suggests a fairly dense surrounding medium. While the shock itself is most dramatic in high-energy bands like X-rays, its presence hints at a complex, possibly turbulent local environment that might be rich in plasma or dust. If Jaminga's own neighborhood contains a cocoon of ionized or neutral material, it could serve as a localized radio filter, effectively blocking lower energy waves from escaping. Some researchers have proposed that such absorption might not be constant, but episodic. The ISM is not a uniform cloud. It contains filaments, bubbles, and density variations on a wide range of scales. If Jaminga's path has taken it through a particularly radio-opaque region, say, a molecular cloud or dense ionized shell, then its radio signal may have been temporarily extinguished for the duration of its passage. In this case, the radio silence may not be permanent. It may be seasonal on astronomical timescales. Efforts have been made to test this hypothesis by studying the dispersion measures and absorption properties of nearby pulsars. If a neighboring pulsar along a similar line of sight shows strong dispersion or reduced flux, that might imply a common foreground structure that could also be affecting Jaminga. However, results have been inconclusive. Some pulsars in the vicinity are detected just fine in the radio band, while others are weaker than expected. This patchwork result makes it difficult to definitively rule in or out absorption as a primary cause. Additionally, radio telescopes operating at higher frequencies, above the range where absorption is most effective, have also failed to detect Jaminga. This is a critical point. If absorption alone were responsible, we might expect the signal to reappear at higher frequencies, which are less prone to interstellar interference. But even these searches have come up mostly empty, weakening the case for absorption as the sole explanation. That said, this doesn't entirely eliminate the possibility. It could be that absorption is acting in combination with other factors. For example, Geminga's radio beam could already be weak or narrowly directed, and what little radiation does head toward us is then filtered or scattered by the ISM. In this layered interpretation, Geminga's silence becomes not the result of one overwhelming cause, but a quiet collaboration between several subtle ones. There's even speculation that local absorption effects might originate from material ejected during Geminga's formation. When the original supernova explosion occurred around 300,000 years ago, it likely expelled a vast amount of gas and dust into space. Some of this material could still linger in the vicinity, gradually dispersing but still thick enough in parts to affect radio transmissions. If we're observing Jaminga through this residual cloud, we may be seeing the ghost of the supernova itself interfering with our attempts to hear the neutron star it left behind. Instruments like the Very Large Array, VLA, and LOFAR, the low-frequency array in Europe, have been deployed in the search for ultra-low-frequency radio emissions from Jaminga, which might behave differently in terms of scattering and absorption. These studies have pushed detection limits to their extreme, but so far, they have not turned up convincing evidence of a buried signal. However, the sensitivity of such arrays continues to improve, and future generations of radio telescopes, such as the Square Kilometer Array, SKA, may finally be able to peer through the fog of the ISM and settle the question. In the grand tapestry of astrophysics, the absorption hypothesis serves as a reminder that space is not empty. It is filled with matter, tenuous, dynamic, and often invisible, that can shape the signals we receive from even the most powerful celestial objects. If Jaminga's radio voice has been muffled, it may not be its fault at all. The universe itself may be getting in the way, placing a veil of plasma and dust between us and one of the galaxy's most intriguing messengers. Jaminga's story becomes even more fascinating when we examine two of its fundamental physical properties: how fast it spins, and how long it's been spinning. These two metrics, its rotational period and its estimated age, not only tell us what Jaminga is doing now, but also offer a glimpse into its turbulent past and the journey it has taken through the galaxy. Jaminga's spin period is approximately 237 milliseconds. That means this neutron star, barely 20 kilometers in diameter, completes one full rotation on its axis in just under a quarter of a second. This rate of rotation is both incredibly fast and yet relatively moderate by pulsar standards. Some neutron stars, particularly younger ones or those that have been spun up in binary systems, can rotate hundreds of times per second. Those are known as millisecond pulsars. Others, older and more fatigued by cosmic time, spin once every few seconds. Jaminga falls somewhere in between, spinning a little over 4 times each second, like a cosmic gyroscope steadily maintaining its momentum across the void. This spin is not just an arbitrary number, it's the heartbeat of the pulsar. As Jaminga rotates, its magnetic field drags around charged particles and generates beams of electromagnetic radiation, particularly in the gamma-ray and X-ray parts of the spectrum. These beams sweep through space in a lighthouse-like manner, and every time they align with Earth, we detect a pulse. In Jaminga's case, those pulses arrive every 237 milliseconds in gamma rays, but not in radio, as we've discussed. Now, this spin isn't constant. Like all pulsars, Jaminga is gradually slowing down. The mechanism behind this slowdown is the loss of rotational energy, emitted as radiation and as a relativistic wind of particles. By precisely measuring the rate at which its spin period is increasing, that is, how quickly it's losing rotational speed, astronomers can estimate how long Jaminga has been spinning down since it was born in the aftermath of a supernova explosion. This method, known as spin-down age estimation, is not exact, but it offers a useful approximation. Using this technique, Jaminga is estimated to be around 300,000 years old. That's remarkably young in stellar terms. For comparison, our Sun is 4.6 billion years old. In that context, Jaminga is a newborn, an infant still glowing from the violence of its birth. But in the lifetime of pulsars, it's already well into its adolescence. It has spun down from what was likely a much faster rotation rate at birth. It has left behind its supernova remnant, and now it races silently through the galaxy, trailing a glowing wake of high-energy particles. This age estimate also correlates with other data. Jaminga's motion through space is exceptionally fast, estimated at over 200 kilometers per second. If we track this back in time, it seems to originate from a region of the sky in the constellation Gemini, close to where the original supernova explosion would have occurred roughly 300,000 years ago. That connection even ties into the name, Jaminga, which we'll explore more deeply in the next segment. What's especially interesting about this age is how it positions Jaminga in the broader pulsar life cycle. Pulsars are typically born spinning rapidly, anywhere from a few milliseconds to a few tens of milliseconds per rotation. Over hundreds of thousands to millions of years, their magnetic dipole radiation and particle winds gradually sap their rotational energy, causing them to slow. Eventually, many pulsars spin down so much that they fall below the death line, a point at which they can no longer sustain the processes that produce coherent radio emission. When that happens, they effectively turn off as radio pulsars, even though they may continue to emit weakly in other bands or become invisible entirely. Jaminga appears to be somewhere along that evolutionary path. It's no longer fast enough to be a young, vibrant radio beacon, but it's still energetic enough to generate intense gamma rays and X-rays. This transitional phase makes it invaluable to scientists trying to understand the full life cycle of neutron stars. How does a pulsar evolve from a brilliant, fast-spinning young object to a cold, quiet remnant? Jaminga provides a real-time case study, one of the few where we can observe a pulsar in this in-between state. Its spin also tells us something about its magnetic field. The process of slowing down a pulsar is driven largely by its magnetic dipole. In Jaminga's case, the strength of its magnetic field, inferred from its spin-down rate, is estimated to be around 1.6 times 10 superscript 1 superscript 2 Gauss, an unimaginably strong field by human standards, but typical for a middle-aged pulsar. This field plays a crucial role not just in emitting radiation, but also in shaping the pulsar wind and forming the bow shock and trailing tail of particles we observe in X-rays. The combination of spin and magnetism is what defines a pulsar, and in Jaminga, that combination remains active, powerful, and enigmatic. Jaminga's age also speaks to its isolation. Unlike many pulsars that reside in binary systems, especially the older ones that have been recycled by accreting material from a companion, Jaminga travels alone. If it was ever part of a binary, that relationship was destroyed in the supernova explosion that birthed it. More likely, though, it was a solitary massive star to begin with, and it remains solitary as a neutron star. That solitude means its age can't be masked or altered by the complex dynamics of a companion's influence, making it a more straightforward subject for studying pulsar evolution. So in Jaminga's rotation and age, we find not just numbers, but a narrative, a story of a star that once burned bright, collapsed in an instant, and has been whispering its story through high-energy light ever since. It spins on, slowly and steadily, marking the time since its fiery birth and offering us clues to the behavior of neutron stars across the ages. Its 237 millisecond rhythm is the tick of a cosmic clock, and its 300,000-year history is a chapter still being written with each passing pulse. In the grand scale of the cosmos, where even our nearest neighboring stars are light years apart, the distance between Earth and Jaminga becomes a striking point of interest. Located approximately 800 light-years away, Jaminga is one of the closest known neutron stars to our solar system, a nearby cosmic neighbor hiding in the darkness. Its proximity adds an intriguing layer to the mystery and importance of this peculiar object. It's not just distant and abstract, it's relatively close in our galactic backyard, silently radiating in gamma rays and X-rays, all while refusing to reveal itself in the radio spectrum. To understand why 800 light-years is considered close, we have to consider the structure of our galaxy. The Milky Way spans about 100,000 light-years in diameter, containing over 100 billion stars. Neutron stars, particularly observable ones, are comparatively rare, scattered throughout the disk and halo of the galaxy. Many known pulsars lie thousands, sometimes tens of thousands, of light-years away. For a neutron star to be just 800 light-years from us means that, on the scale of galactic cartography, it's practically next door. This closeness means a few very important things. First, it allows astronomers to study Jaminga with greater detail than more distant objects. Gamma-ray and X-ray emissions, although energetic, still diminish with distance. The closer the source, the more photons we can collect, and the more precise our measurements become. For Jaminga, this has allowed scientists to track not just its pulsations, but also its proper motion, how it physically moves across the sky over time. Observations from instruments like Rosat and Chandra have actually revealed this motion, allowing astronomers to trace Jaminga's path backward through space, giving insight into its origin and how it has traversed the galaxy since its supernova birth. Its proximity has also helped in detecting and studying its pulsar wind nebula, the glowing tail it leaves as it barrels through the interstellar medium. These tails and bow shocks are difficult to observe in distant pulsars due to their faintness and small apparent size. But for Jaminga, even subtle emissions become accessible, letting us see how the pulsar interacts with its surroundings. The data extracted from these emissions contributes to our broader understanding of how neutron stars shape and energize their environment, distributing high-energy particles and magnetic fields into the galactic medium. Moreover, the nearness of Jaminga makes it a prime candidate for investigating its possible contribution to local astrophysical phenomena, especially in the case of high-energy cosmic rays. Some models suggest that Jaminga, because of its age, spin-down power, and proximity, might be contributing a significant amount of energetic electrons and positrons to the space around Earth. These particles, traveling through interstellar space, could be reaching us and influencing the flux of cosmic rays detected by instruments on Earth and in orbit. In fact, certain anomalies in the observed positron fraction, such as those seen by the AMS-02 experiment on the International Space Station, have sparked speculation that Jaminga, along with another nearby pulsar called Monogem, could be responsible. It's a tantalizing thought that invisible radiation bathing our atmosphere might have originated in this silent object just a few hundred light-years away. Additionally, its relative closeness also raises provocative questions about what we might still be missing. If an object as exotic and unique as Jaminga lies this close to us, how many more such radio-quiet, gamma-loud neutron stars are lurking in the nearby galaxy, hidden from view simply because we haven't looked with the right instruments or in the right wavelengths? It underscores the potential existence of an unseen population of Jaminga-like pulsars, enigmatic stars that don't follow the usual playbook and remain undetected in traditional radio surveys. The proximity of Jaminga also has implications for the history of our region of the Milky Way. Every neutron star is born from a supernova, and Jaminga's presence suggests that around 300,000 years ago, a massive star exploded relatively close to our solar system. That supernova would have been bright enough to outshine the moon for days or weeks, visible in the skies of prehistoric Earth. There's even speculation that this explosion may have left traces on our planet, possibly in the form of isotopic anomalies in ice cores or deep-sea sediments, though no direct connection has yet been made. Furthermore, being only 800 light-years away means Jaminga is within reach of future missions designed to explore the nearby galaxy in even finer detail. With the coming generations of space telescopes and high-energy observatories, like the Cherenkov Telescope Array, Athena, and even speculative gravitational wave detectors optimized for neutron stars, we may be able to probe Jaminga's surface, its magnetic field, and its emissions in unprecedented depth. It may eventually become one of the most studied neutron stars simply because it's so close, offering a kind of cosmic laboratory just waiting for the right instruments to explore it. Its location also brings it into our collective imagination in a more visceral way. When we look up into the night sky, we can roughly point in the direction of Gemini, and know that in that otherwise unremarkable section of sky lies a collapsed stellar core, an object so dense that a teaspoon of its material would weigh more than Mount Everest. It spins silently, sends high-energy pulses of light screaming through space, and might even be shaping the particle environment around our solar system. And it's doing all of this just 800 light-years away, close enough to be a familiar presence, yet still cloaked in mystery. Jaminga's proximity isn't just a spatial fact, it's a gateway to insight. Because it's so close, we're afforded a sharper view of an otherwise elusive type of cosmic object. It reminds us that even in our relative celestial neighborhood, the universe harbors enigmas that challenge our understanding and push the limits of our scientific models. And unlike other nearby stars that we see shining brightly in optical light, Jaminga exists as a ghostly presence, observable only in the highest energies, invisible to our eyes but profoundly real in its effects and presence. In the quiet proximity of Jaminga, we find the perfect paradox. It's nearby yet hidden. It's silent in radio, yet deafening in gamma rays. It doesn't shine like ordinary stars, yet it lights up the detectors of our most advanced observatories. This neutron star is not just a remote scientific curiosity, it's a neighbor, quietly watching, silently pulsing, whispering its ancient story in the language of light invisible to the human eye. As Jaminga sprints through the galaxy at supersonic speeds, it does not move silently or without trace. On the contrary, this neutron star carves a path across the fabric of space like a cosmic speedboat slicing through a calm lake, leaving behind a wake of glowing particles. This phenomenon is known as the Jaminga Trail, a shimmering tail of high-energy X-ray emissions that extends behind the pulsar, visible thanks to advanced space observatories. It's one of the most visually compelling and scientifically fascinating features associated with Jaminga, offering profound insights into both its motion and its interaction with the interstellar medium. This trail was first resolved with clarity using the XMM Newton and Chandra X-ray observatories. These instruments allowed astronomers to image the elongated, asymmetric cloud of X-rays trailing behind Jaminga, confirming not only the direction of its motion but also the incredible energy it pours into the space around it. The trail is not just a passive signature, it is an active interaction between the pulsar's powerful wind and the surrounding interstellar gas, driven by the immense velocity of the neutron star. Jaminga is estimated to be moving at about 200 kilometers per second, which is fast enough to outpace the speed of sound in the interstellar medium. This makes it a supersonic object, generating a bow shock in front of it and leaving behind a turbulent wake. As the pulsar's powerful magnetic field whips around, it accelerates particles, mainly electrons and positrons, to nearly the speed of light. These high-energy particles spiral around magnetic field lines, emitting synchrotron radiation as they go. This radiation is what creates the extended X-ray glow, essentially painting Jaminga's path across the stars. This glowing trail is not uniform, it exhibits structure. In some images, the trail appears forked or segmented, suggesting complex magnetic interactions or varying densities in the surrounding space. In fact, Jaminga's trail has been observed to stretch several light-years behind it, suggesting an energetic process that sustains itself long after the pulsar has moved on from any given location. This means that even as the neutron star races forward, it leaves behind a kind of energetic footprint, a luminous memory in the sky. The orientation of the trail also helps scientists confirm Jaminga's proper motion, as its direction aligns perfectly with the path the neutron star has been measured to follow over decades of observation. This reinforces our understanding of its kinematics and origin. Tracing the trail backward also helps astronomers pinpoint where the original supernova might have occurred roughly 300,000 years ago, giving insight into the stellar nursery from which Jaminga emerged. More intriguingly, the trail is not just a passive relic, it may also be a source of cosmic rays. The electrons and positrons streaming out from Jaminga's poles, flung into space at relativistic speeds, contribute to the sea of high-energy particles that permeates our galaxy. Some of these particles may reach Earth, and this connection has fueled theories suggesting that Jaminga is partly responsible for certain high-energy anomalies detected in our local cosmic ray environment. In recent years, this idea gained more attention when telescopes like HAWC, High-Altitude Water Cherenkov Observatory, detected a TeV halo, a vast region of very high-energy gamma rays surrounding Jaminga. This halo extends dozens of light-years and is thought to be a consequence of the same relativistic particles that formed the X-ray trail. It appears that Jaminga's energetic emissions don't just leave a glowing tail. They ripple out in all directions, forming a vast zone of influence in its vicinity. These emissions hint at how energy propagates from neutron stars into the broader galactic environment, offering a laboratory for understanding particle diffusion, magnetic field interaction, and shock front dynamics. From a visual perspective, the trail is poetic, a glowing scar in the void, marking the passage of something ancient and violent. It's a silent testimony to the force of the supernova explosion that launched Jaminga into space, and a record of the continual power being released as the pulsar spins, emits, and interacts with the cosmos. If you could see in X-ray wavelengths, the trail would be like a shimmering river stretching across the heavens. In this context, the Jaminga Trail is more than just an interesting feature. It's a narrative structure, telling the story of the neutron star's birth, its journey, and its ongoing influence. It is physical evidence of movement and of interaction, a rare cosmic breadcrumb path leading to a deeper understanding of how neutron stars behave, evolve, and communicate with the galaxy around them. Furthermore, studying the trail provides insight into the pulsar wind nebulae (PWN) mechanism. Many young and energetic pulsars are surrounded by nebulae formed by particles accelerated by the pulsar wind. However, Jaminga doesn't have a classic spherical nebula. Instead, it has this streamlined, comet-like trail, a product of its high speed and unique emission dynamics. By comparing it with other PWN, astronomers are refining their models of how particle acceleration and magnetic fields operate in such extreme environments. Jaminga's trail is like a scaled-down, highly directional variant of these nebulae, showing what happens when a pulsar doesn't just sit within a cloud of gas but moves rapidly through it. In all, the Jaminga Trail is an essential piece of the puzzle. It bridges the gap between the unseen and the observable, between theoretical models and actual data. It links the pulsar's violent beginnings to its ongoing legacy. And it paints a picture not just of Jaminga as a point in the sky, but as a dynamic actor in the galactic stage, constantly shaping and reshaping the space it moves through. As it continues its journey through the galaxy, the trail will evolve, stretching further, fading perhaps, or interacting with new clouds and fields. It will continue to glow for thousands, maybe millions of years, long after our instruments can detect it, and perhaps long after humanity has moved beyond this epoch of exploration. But for now, it serves as a glowing reminder that even in silence, Jaminga leaves a profound mark on the universe. As Jaminga hurtles through the galaxy, its incredible velocity doesn't just stir the space behind it, it slams into the interstellar medium ahead of it, creating a dramatic and powerful interaction known as a bow shock. This is not unlike the shockwave that forms in front of a supersonic jet as it breaks the sound barrier in Earth's atmosphere. But here, the medium isn't air. It's the sparse mix of gas and plasma that fills the spaces between stars. And the speeds involved, though not light speed, are enough to cause astonishing high-energy effects across multiple wavelengths of light. This bow shock is the result of the pulsar wind, a flow of charged particles, mainly electrons and positrons, being expelled at nearly the speed of light from the magnetic poles and outer regions of the neutron star. These particles are accelerated by Jaminga's intense magnetic field and rotation. As Jaminga travels supersonically, this wind doesn't simply drift away, it collides head-on with the surrounding interstellar medium. The resulting friction and pressure gradient cause particles to decelerate, pile up, and heat the surrounding material, creating a visible arc of emissions. This is the bow shock. The shape of this bow shock is highly dynamic, influenced by Jaminga's speed, direction, and the density of the material in its path. Observations have shown a curved, comet-like shape pointing in the direction of Jaminga's travel, with a narrower head near the pulsar and a more diffuse tail trailing behind. This structure glows faintly but detectably in X-rays and gamma rays, and forms the front line of interaction between Jaminga and the galaxy. In many ways, the bow shock functions like a galactic test chamber. Here, we witness relativistic particles being braked, compressed, and redirected by a moving obstacle, namely, the interstellar gas. This environment provides a natural laboratory for studying plasma physics, particle acceleration, and magnetic turbulence under extreme conditions that cannot be replicated on Earth. It's in these shock zones that astronomers believe particles can be reaccelerated, potentially to energies sufficient to contribute to the galactic population of cosmic rays. What's especially interesting is how different the bow shock is from the structures seen around slower-moving or younger pulsars. In those cases, the pulsar wind can inflate a roughly spherical bubble known as a pulsar wind nebula, PWN. But with Jaminga, its high velocity deforms this bubble, forcing it into a compressed front and a tightly collimated, elongated trail. This tells scientists that speed is not just a kinematic detail. It fundamentally alters the way pulsars interact with their environment. The physics behind this can be broken down into several key components. First, the termination shock occurs where the outflowing pulsar wind abruptly slows down as it hits the surrounding interstellar medium. This deceleration causes a compression of particles and magnetic fields, which then emit synchrotron radiation. This is part of what makes the bow shock and trail visible. Beyond the termination shock is the contact discontinuity, where the shocked wind meets the shocked interstellar medium. Further out is the forward shock, the outermost layer where the onrushing pulsar compresses and heats the interstellar gas ahead of it. These layered structures aren't just theoretical. They have analogues in other pulsars and in detailed simulations of astrophysical shocks. Jaminga's bow shock has been analyzed using data from the Chandra X-ray Observatory, which has the resolution to distinguish fine structures in the immediate vicinity of the neutron star. Some images suggest not just a single bow shock, but multiple arc-like features that could be ripples or instabilities forming in the compressed plasma. These features might arise from changes in the ambient interstellar density or fluctuations in Jaminga's own wind output. There's also compelling evidence that the geometry of the bow shock aligns with the broader direction of the Jaminga trail, showing that both phenomena are part of a coherent interaction shaped by Jaminga's motion and emission. The bow shock, therefore, is not just an isolated structure. It feeds energy and particles into the trail behind, creating a feedback loop that stretches across several light years. Moreover, this bow shock is part of why Jaminga might be a contributor to Earth's local high-energy particle environment. When the accelerated particles within the bow shock and trail escape the region, they can diffuse into the surrounding interstellar space. If the orientation is right, and given Jaminga's relative proximity, it likely is, some of these particles could make their way to our solar system. In fact, observations by the High-Altitude Water Cherenkov (HAWC) observatory suggest that the extended halo of gamma-ray emissions surrounding Jaminga, which is linked to these very same relativistic particles, may be a persistent source of TeV-scale cosmic rays. This association strengthens the idea that Jaminga's bow shock and wind trail are not merely localized curiosities. They could be part of a much larger system influencing the high-energy environment of our region of the galaxy. In theoretical models, the interaction between pulsar wind and interstellar medium is governed by magnetohydrodynamics, MHD, a branch of physics that combines the principles of magnetism and fluid dynamics. In this framework, the pulsar wind is modeled as a magnetized plasma jet, and its interaction with the ambient gas gives rise to complex wave structures, instabilities, and field reversals. By observing Jaminga's bow shock, astrophysicists can refine these MHD models, tuning them to better match the observed shapes, sizes, and brightness variations. The bow shock is also useful as a tracer for time. Since we know the speed at which Jaminga is moving, and we can measure the length of its bow shock and trail, scientists can back-calculate how long this interaction has been happening. These calculations support the idea that Jaminga has been blazing through space for hundreds of thousands of years, since its supernova origin in the local Orion arm of the Milky Way. One of the most profound implications of this structure is the notion that Jaminga is not just an astronomical object, but an agent of change. Its bow shock compresses, heats, and possibly seeds star formation in nearby gas clouds. It injects energy into the interstellar medium, creating turbulence and spreading relativistic particles. It effectively shapes its galactic neighborhood, and it's one of the very few systems where we can directly observe such influence in high-energy wavelengths. In sum, Geminga's supersonic pulsar wind and bow shock form one of the most dramatic features associated with this enigmatic object. They offer scientists an unparalleled view of high-energy astrophysical processes in action. The combination of relativistic winds, shock interactions, particle acceleration, and radiative trails make Jaminga a jewel of cosmic dynamics, a system as active as it is mysterious. In many ways, Jaminga is more than a celestial object. It's a natural laboratory, a vast arena in space where the laws of physics are pushed to their most extreme limits. It's a high-energy crucible where matter, radiation, and magnetic fields interact in ways that are impossible to replicate on Earth. As such, it offers an invaluable window into the workings of exotic physics, especially in the realm of particle acceleration, quantum electrodynamics, and magnetohydrodynamics in extreme environments. At the heart of this laboratory is the neutron star itself, born from the collapsed core of a massive star that once ended its life in a supernova explosion. This remnant, though no larger than a city in size, contains more mass than our entire Sunday. The gravitational field at its surface is so intense that it bends space-time significantly, and the magnetic fields it carries are trillions of times stronger than Earth's. These conditions set the stage for some of the most powerful natural accelerators in the universe. Jaminga is what's known as a rotation-powered pulsar. It emits energy as it slows its spin over time, converting rotational kinetic energy into high-energy radiation. As Jaminga rotates, roughly once every 237 milliseconds, it whips its intense magnetic field around with it, accelerating charged particles to near-light speeds in the process. These particles are ejected in the form of a pulsar wind composed of electrons, positrons, and possibly even heavier nuclei. These accelerated particles interact with the surrounding magnetic and electric fields, emitting radiation across the spectrum through a variety of processes. One of the most important of these is synchrotron radiation, which occurs when charged particles spiral along magnetic field lines at relativistic speeds. The radiation produced in this way is typically found in the radio to X-ray range, and in Jaminga's case, it contributes to the glowing X-ray trail and bow shock we observe. Then there's inverse Compton scattering, another hallmark of high-energy astrophysics. This occurs when high-energy electrons collide with lower-energy photons, like those from the cosmic microwave background or local starlight, and impart energy to them, effectively boosting them into the gamma-ray regime. Jaminga's powerful winds of relativistic electrons provide exactly the kind of environment where this process thrives. It's one reason why the gamma-ray emissions from Jaminga are so intense, despite the absence of a strong radio signal. But beyond radiation, Jaminga is a testing ground for how particles gain their extreme energies in the first place. One of the biggest mysteries in modern astrophysics is the origin of cosmic rays, those high-energy particles that zip through the galaxy and occasionally collide with Earth's atmosphere. Some are so energetic that they defy current models of acceleration. Pulsars like Jaminga are prime suspects for the source of a significant portion of these cosmic rays, especially in the TeV, tera-electronvolt, energy range. Observatories like HAWC and Fermi have detected gamma-ray halos around Jaminga that suggest these particles are indeed escaping and diffusing into the local galactic environment. This leads to the idea that Jaminga may be surrounded by a sort of TeV halo, a vast cloud of ultra-relativistic particles that extends light-years from the pulsar itself. These halos are believed to form when particles accelerated near the pulsar escape and scatter off magnetic irregularities in the interstellar medium. The size, brightness, and diffusion rate of this halo offer direct clues about how cosmic rays propagate through the galaxy. And since Jaminga is one of the nearest pulsars to Earth, only about 800 light-years away, it's ideally positioned to affect the local interstellar environment, and perhaps even the cosmic ray flux reaching our solar system. In modeling these processes, physicists use the frameworks of relativistic magnetohydrodynamics, RMHD, a synthesis of Maxwell's equations and fluid dynamics adapted to extreme, relativistic conditions. Jaminga offers a perfect subject for testing these models in real time. The structures in its bow shock, the variability in its trail, and the spectrum of its emissions all provide data points that refine these theoretical constructs. Without real-world examples like Jaminga, much of our understanding of RMHD would remain purely speculative or dependent on simulations alone. Then there's the matter of quantum electrodynamics, QED, in strong fields. In Jaminga's magnetic environment, electrons are subject to field strengths approaching or even exceeding the Schwinger limit, the theoretical point where the vacuum itself becomes unstable and starts producing particle-antiparticle pairs. While Jaminga's fields aren't quite at this limit, they're close enough that they help scientists study how matter and energy behave in the presence of ultra-strong fields, a realm not accessible in any Earth-bound particle accelerator. Moreover, the complexity of Jaminga's magnetosphere, the region around the pulsar dominated by its magnetic field, offers another avenue of high-energy physics investigation. Magnetospheric models attempt to explain how charged particles move, accelerate, and radiate in this highly dynamic and nonlinear space. Unlike many other pulsars, Jaminga's lack of radio emission means that its magnetosphere must be analyzed primarily through its gamma and X-ray behavior. This forces a rethinking of existing models, which often assume a correlation between radio and high-energy emissions. In this sense, Jaminga isn't just helping science progress, it's challenging its assumptions. Even more fascinating is the possibility that Jaminga could harbor transient processes we've yet to detect. For instance, sudden reconnection events in its magnetic field, akin to solar flares on the Sun, but vastly more powerful, might briefly accelerate particles to ultra-high energies or even emit bursts of gravitational waves. While no such events have yet been definitively observed from Jaminga, its peculiar profile and isolation from other sources of interference make it a prime candidate for long-term monitoring. Finally, Jaminga offers a rare look into the evolution of neutron stars over hundreds of thousands of years. It stands as a transitional object, old enough to have lost much of its initial rotational energy, but still energetic enough to power high-energy emissions. Studying how its emission profile has changed over time, something scientists attempt by modeling historical data and extrapolating backwards, gives us insights into the life cycle of pulsars. This helps create a unified understanding of how a young, rapidly spinning pulsar transitions into a quieter, older object, possibly even cooling into invisibility over millions of years. All told, Jaminga is not just a case study, it's a benchmark. A unique combination of proximity, isolation, and high-energy activity make it the perfect subject to test our understanding of physics under conditions we can't replicate anywhere else. It reveals the mechanics of acceleration, radiation, diffusion, and magnetic field interactions with a clarity that is hard to find elsewhere in the cosmos. In the end, this silent neutron star may never speak in radio, but its gamma-ray voice tells us volumes about the universe's deepest laws. Every photon it emits is a messenger from the frontier of physics, carrying news from a place where the ordinary rules break down and a more exotic version of reality emerges, brighter, faster, and far more mysterious. One of the most compelling reasons scientists continue to study Jaminga with such intensity is its suspected link to a much larger cosmic phenomenon, high-energy cosmic rays that continually bombard Earth from space. These cosmic rays, mostly made of protons and atomic nuclei, have puzzled physicists for decades. Where do they come from? How do they gain such enormous energy? And why do we see more of them coming from certain directions in the sky? Jaminga might hold a significant piece of this galactic puzzle. For a long time, supernova remnants were thought to be the primary source of galactic cosmic rays. These remnants, expanding shells of gas left over from exploded stars, can indeed accelerate particles through shock waves. But over time, it became clear that supernova remnants alone might not fully account for the observed energy levels, particle types, or spatial distributions of cosmic rays, especially those in the TeV, tera-electronvolt, energy range, and beyond. That's when astrophysicists began to look more closely at pulsars, and specifically at Jaminga. Jaminga is a particularly promising candidate for cosmic ray production because it's relatively close to Earth, only about 800 light-years away. It also has the right age, around 300,000 years old. That means the cosmic rays it emitted during its more active early period could have had enough time to travel across interstellar space and reach us today. And unlike other sources that are buried deep in crowded regions of the galaxy, Geminga lies in a relatively clean neighborhood of space, allowing scientists to observe its influence with fewer interfering factors. So how could a pulsar like Geminga create cosmic rays? It all comes down to its pulsar wind nebula and its powerful rotating magnetic field. As the neutron star spins, it generates enormous electric fields that accelerate electrons and positrons to relativistic speeds. These charged particles stream out into space, forming a so-called pulsar wind. Over time, some of these particles can escape the immediate vicinity of the pulsar and begin diffusing outward, eventually mixing with the interstellar medium and making their way toward Earth. In the case of Jaminga, this theory gained serious traction in 2017 when data from the High-Altitude Water Cherenkov (HAWC) Gamma-ray Observatory revealed an extended halo of TeV gamma rays surrounding the pulsar. This was huge. It indicated that ultrarelativistic electrons and positrons were being accelerated by Jaminga and then colliding with background photons, most likely from the cosmic microwave background, through inverse Compton scattering. These collisions boosted the photons to gamma-ray energies, lighting up the surrounding region in a massive, ghostly glow. This gamma-ray halo is not only visually striking but also physically revealing. Its size and brightness suggest that a significant population of energetic particles is escaping Jaminga and diffusing outward. What's even more intriguing is that the diffusion rate in this halo appears to be much slower than expected, meaning that the interstellar medium around Jaminga is somehow trapping these particles more effectively than typical galactic environments. This could mean that Jaminga's contribution to the local cosmic ray population is higher than previously thought. Why does this matter for Earth? Because about a decade ago, scientists observed an unexpected excess of high-energy positrons in cosmic ray measurements made by experiments like Pamela, AMS-02, and Fermi-LAT. These positrons, essentially the antimatter counterpart of electrons, were arriving at Earth in greater numbers than predicted by traditional models of cosmic ray propagation and decay. At first, this anomaly led to wild speculation, including ideas involving dark matter annihilation. But a more grounded and plausible explanation soon emerged. Pulsars like Jaminga could be emitting large numbers of these positrons, and their relative proximity could explain the observed excess. In this framework, Jaminga becomes not just an astrophysical curiosity, but a primary suspect in the case of the missing positrons. Its spin-down energy, emission rate, and distance align neatly with the requirements for producing the observed cosmic ray flux. If true, this would be a monumental confirmation of pulsars as local sources of high-energy cosmic rays, a conclusion that ties together observations across multiple wavelengths and decades. And yet, even this idea has complications. For one, the unusually slow diffusion rate detected by HAWC suggests that the positrons from Jaminga may not actually reach Earth in the numbers required to explain the positron excess, at least, not under conventional diffusion models. This has sparked a wave of new theoretical work. Some researchers suggest that the region of slow diffusion may be limited to a small halo around Jaminga, with faster diffusion rates taking over beyond that. Others are reworking models of cosmic ray propagation to include more localized structures and anisotropies in the interstellar medium. To validate or challenge these theories, astronomers are now looking for similar halos around other pulsars. So far, Monogem, another relatively nearby pulsar, has shown similar features, which strengthens the case for a broader class of middle-aged, radio-quiet gamma-ray pulsars playing a crucial role in shaping the local cosmic ray environment. These findings are also pushing observatories to look more deeply into TeV gamma-ray mapping, as these halos provide a kind of fingerprint of particle acceleration and escape. But even if Jaminga doesn't account for the entire positron excess on its own, it unquestionably serves as a proof of principle. It shows that isolated pulsars can accelerate particles to extreme energies and inject them into the galaxy in ways we're only beginning to understand. And in doing so, it becomes a linchpin in the larger quest to trace the origins and behavior of cosmic rays, one of the most enduring mysteries in astrophysics. Jaminga, in this sense, is like a smoking gun left behind after a cosmic crime. The bullet, high-energy particles, is long gone, but the glowing evidence remains. It tells a story not only about how neutron stars evolve, but also about how the galaxy itself is seeded with energetic matter. It connects the dots between the birth of stars, the death of giants, and the invisible but powerful particles that rain down on us every day from the deep sky. And in the process, it elevates this silent, radio-quiet object into a key player in one of the most dynamic, energetic, and enigmatic processes in the cosmos. As detectors grow more sensitive and our models grow more precise, the role of Geminga in the cosmic rain narrative will only become clearer. But even now, it whispers through gamma rays and positrons, giving us tantalizing hints of the vast, unseen network of energy that threads through our universe. If Jaminga has taught astronomers anything, it's this: what we don't hear might still be very much there. Jaminga's existence as a radio-quiet but gamma-bright pulsar opens the door to a profound and unsettling realization. There may be many more such objects scattered throughout the Milky Way, quietly spinning, emitting torrents of high-energy particles and radiation, yet completely invisible to the traditional tools that first brought pulsars into the spotlight. For decades, radio astronomy served as the primary method for discovering pulsars. This made sense because pulsars were first identified by their periodic radio pulses, and the infrastructure for detecting such emissions was well developed. Large radio dishes like the Arecibo Observatory, Parkes Telescope, and the Green Bank Telescope were finely tuned to scan the skies for the telltale tick-tick-tick of rotating neutron stars beaming narrow pulses of radio energy at Earth. Over 2,000 pulsars have been catalogued using this method. And yet, the very existence of Jaminga, completely invisible in radio, yet a loud voice in the gamma-ray domain, suggests our census of pulsars might be far from complete. Jaminga was hiding in plain sight. Its gamma-ray brilliance had been detected as far back as the 1970s, but it took decades of coordinated observations across multiple wavelengths to identify it for what it truly was. This long journey of discovery poses a sobering question: how many more neutron stars are out there, invisible to radio telescopes, escaping detection simply because they do not emit in a band we initially prioritized? Gamma-ray observatories like NASA's Fermi Gamma-ray Space Telescope have been instrumental in uncovering this hidden class of neutron stars. Since its launch in 2008, Fermi has identified dozens of unassociated gamma-ray sources, point-like sources of high-energy radiation for which there was no clear counterpart in radio, optical, or even X-ray data. Over time, careful analysis has shown that many of these unassociated sources share properties with Jaminga: pulsed gamma-ray emission, lack of a radio counterpart, and isolated locations in the sky. These are now known as gamma-ray selected pulsars, and they hint at an unseen population that may rival or even outnumber the traditional radio-detected class. The implications are far-reaching. If Jaminga-like objects are abundant, it could mean that pulsars are a much more common evolutionary outcome of massive stars than previously thought. It also reshapes our understanding of neutron star demography. The pulsar population may be heavily biased by observational selection effects, not just in wavelength but in beam orientation, distance, and surrounding environment. One of the main theories explaining Jaminga's radio silence is that its radio beam simply doesn't intersect Earth. This beaming geometry hypothesis implies that we're only seeing a fraction of the pulsar population whose beams happen to point at us. If pulsar beams are narrow cones and they rotate like lighthouses, the Earth must lie within the sweep of that beam in order to detect the signal. This means that a potentially vast majority of neutron stars are flying under the radar, simply because their beams don't sweep past our planet. This becomes even more plausible when you consider that gamma rays, being produced farther out in the magnetosphere, may originate from broader beams. That means that gamma ray emission could be more omnidirectional, making gamma-ray telescopes like Fermi better suited to catch pulsars regardless of their beam orientation. If that's the case, then Fermi may be peeling back the curtain on a cosmic iceberg whose visible tip, the radio pulsars, belies a much more expansive and active hidden structure below the surface. Moreover, some of these radio-quiet pulsars might not be entirely radio-silent. They could emit in radio, but at levels too faint for current instruments to detect. Or their emission could be intermittent, variable, or masked by the interstellar medium. The notion of nulling pulsars, whose radio pulses switch on and off, adds another layer of complexity to pulsar detection and classification. Jaminga may be just one example of a broader spectrum of neutron star behavior that blurs the lines between categories. There is also the exciting prospect that some radio-quiet pulsars may reside in exotic binary systems, hidden behind thick clouds of gas or even within regions of intense background noise that obscure conventional detections. Some may have properties intermediate between standard pulsars and other exotic neutron stars, such as magnetars, which are known for their powerful magnetic fields and high-energy outbursts, but are also difficult to detect in radio. All of this leads to a tantalizing possibility. Radio-quiet pulsars could be the key to solving other astronomical mysteries. For instance, unexplained gamma-ray sources, local cosmic ray excesses, or even gravitational wave backgrounds might find explanations rooted in this invisible neutron star population. The fact that Jaminga is relatively close to us, only about 800 light-years away, suggests that similar objects could be scattered throughout the Milky Way, and perhaps, much closer than we expect. In fact, simulations of the neutron star population in our galaxy suggest there may be over 100 million neutron stars, most of them undetectable with current methods. Of those, only a tiny fraction has been identified. If even a modest percentage of them behave like Jaminga, bright in gamma rays, quiet in radio, then the known pulsar population could be a severely undercounted sample of the true diversity and abundance of these stellar remnants. The future of uncovering this hidden pulsar population will likely involve a combination of multi-wavelength approaches and novel detection techniques. X-ray missions like NICER and Chandra, in concert with gamma-ray instruments and optical surveys, will be crucial. And as radio technology continues to evolve, particularly with the development of the Square Kilometre Array, SKA, we may finally be able to hear the faint whispers of these ghostly stars. Additionally, advances in machine learning and data mining techniques are helping astronomers reanalyze archival data in search of signals previously missed. Faint pulsations, subtle timing patterns, and hard-to-classify sources are now being revisited with new tools, often revealing features suggestive of previously hidden pulsars. The discovery of each new Jaminga-like object sharpens the profile of this silent majority, and redefines our expectations for what neutron stars can be. In a universe filled with noise, cosmic microwave background, supernovae, black hole mergers, it's ironic that one of the most powerful sources of insight comes from the quietest class of pulsars. They are the still sentinels, the unseen witnesses of stellar cataclysms, whispering across time in the voice of gamma rays and X-rays, bearing clues about matter, space, and energy under conditions we can scarcely replicate on Earth. Jaminga's story may have started as an anomaly, a problem child of astrophysics, but its legacy may well be one of revelation. It has expanded the boundaries of pulsar science and opened the eyes of astronomers to the silent giants among us. If there's anything more humbling in astronomy than what we already know, it's the enormity of what we still don't, and Jaminga is a glowing reminder that the cosmos always has another surprise just beyond the range of our current instruments. As we step further into the modern era of astronomy, the study of objects like Jaminga has been revolutionized by the development of sophisticated gamma-ray observatories. These instruments, orbiting above Earth's atmosphere where gamma rays can be observed unobstructed, have become our most powerful tools in exploring the high-energy universe. And for a pulsar like Jaminga, radio silent, yet ablaze in gamma rays, these observatories are not just helpful, they are essential. The most prominent among them is NASA's Fermi Gamma-Ray Space Telescope, launched in 2008. Fermi's primary instrument, the Large Area Telescope, LAT, was designed specifically to scan the sky for gamma-ray sources, and it has been nothing short of revolutionary. Within weeks of going online, Fermi began picking up pulsed gamma-ray emissions from known sources, and more importantly, it began discovering entirely new classes of pulsars, many of which had no radio signature at all. Jaminga was one of its early targets. With its wide field of view and high sensitivity, Fermi quickly became the go-to observatory for studying pulsars in the gamma-ray domain. And Jaminga, already one of the brightest persistent gamma-ray sources in the sky, became a long-term project for the mission team. Fermi's observations confirmed the pulsed gamma-ray emission pattern of Jaminga, giving researchers unprecedented clarity into its energy output, pulse profile, and emission mechanism. More importantly, Fermi's steady gaze allowed scientists to map how Jaminga's emission varies over time, revealing a complex structure that goes far beyond a simple rotating beacon. Fermi's contributions extend beyond just identifying pulsars. It helped develop a clearer understanding of how pulsars like Jaminga emit gamma rays in the first place. Prior to Fermi, it was uncertain exactly where in a pulsar's magnetosphere these emissions were being generated. The gamma-ray pulses observed by Fermi, in both shape and timing, pointed to emission regions far from the pulsar's surface, likely near the so-called outer gap, or slot gap, regions, which are areas in the magnetosphere where electric fields accelerate particles to nearly the speed of light. These particles then emit gamma rays through curvature radiation and inverse Compton scattering. Fermi's data solidified these models and placed Jaminga firmly in the emerging framework of outer magnetosphere emission, pulsars. But Fermi is not alone in this cosmic endeavor. Other observatories have joined the quest to peel back the high-energy layers of Jaminga's enigmatic behavior. One of the earliest predecessors was the European Space Agency's COSB satellite in the late 1970s and early 1980s, which followed up on the original SAS-2 detection of Jaminga. While COSB couldn't resolve pulsations, it did provide more detailed mapping of the gamma-ray sky, further solidifying Jaminga as a persistent source of high-energy radiation. Following that, the Compton Gamma Ray Observatory, CGRO, which operated from 1991 to 2000, significantly improved our understanding of gamma-ray sources. CGRO's EGRET instrument was able to study Jaminga in greater detail and helped to characterize its gamma-ray spectrum. EGRET's data hinted at pulsed emission, but it wasn't until Rosat's X-ray discovery and subsequent multi-wavelength coordination that these suspicions could be confirmed. Even so, CGRO was a vital link in the chain that led to Jaminga's full classification. In more recent years, Agile, an Italian gamma-ray satellite launched in 2007, also contributed to the study of Jaminga. Although smaller than Fermi, Agile provided complementary data and confirmed many of Fermi's findings, helping to refine models of gamma-ray pulsar behavior and solidify the role of magnetospheric geometry in determining visibility across the spectrum. Each of these instruments brought something new to the table: sensitivity, energy resolution, time resolution, or sky coverage. Together, they have formed an intricate and multi-decade tapestry of data on Jaminga, making it one of the best-studied gamma-ray sources in the sky. Yet, despite all this progress, Jaminga remains curiously aloof. Even Fermi, with its state-of-the-art instruments, cannot answer all the questions. For example, although it captures the broad pulse profile of Jaminga's gamma-ray emission, subtler aspects, such as the detailed polarization of the radiation or the precise location of the emission zones, still elude our understanding. Some of these challenges may only be addressed by future missions with enhanced capabilities. One such proposed mission is the All-Sky Medium Energy Gamma-Ray Observatory, AMEGO, which aims to bridge the gap between hard X-rays and high-energy gamma rays. This is particularly useful for studying transitional emission mechanisms and lower energy processes that may complement our understanding of Jaminga's full emission profile. Similarly, EASTROGAM, a European initiative, is designed to explore the MEV energy band with unprecedented sensitivity, and could provide critical new insights into sources like Jaminga. The reason this continued focus matters is not just about studying one odd pulsar. It's about changing the way we view the entire neutron star population. Every gamma-ray telescope that studies Jaminga helps calibrate our understanding of emission mechanisms across the spectrum. It's also about refining the census of neutron stars, correcting the biases introduced by relying too heavily on radio detection. As more gamma-ray-only pulsars are discovered, Jaminga increasingly stands as the prototype of this class, the silent yet screaming star. What makes this even more exciting is the growing synergy between gamma-ray observatories and other forms of astronomical data. For instance, while gamma-ray observatories provide the raw high-energy signature, X-ray and optical telescopes can give us the motion, environment, and thermal characteristics. This kind of multi-messenger, multi-wavelength approach represents the future of pulsar science. For example, combining gamma-ray data from Fermi with timing measurements from NICER or Newton allows for refined modeling of Jaminga's rotational parameters and even its magnetic geometry. And looking ahead even further, gravitational wave observatories like LIGO and Virgo may eventually detect the trembling echoes of deformed neutron stars, should they emit continuous gravitational waves. Though Jaminga is not currently a prime candidate for this, the theoretical possibility adds another dimension to its mystery. Could there be signals it's emitting that we have not yet developed the instruments to detect? The legacy of Fermi, Agile, CGRO, and the next generation of gamma-ray observatories is profound. They have not only given us a clearer image of Jaminga's character, but they have also exposed the limitations of our earlier assumptions about pulsars. They have shown that neutron stars are not monolithic in behavior but instead represent a spectrum of emission modes, geometries, and evolutionary stages. Jaminga, once a puzzling anomaly, is now a centerpiece in that mosaic, a reminder that the universe doesn't always shout. Sometimes, it sings in a register we weren't prepared to hear, and only now are we tuning in. While gamma-ray telescopes like Fermi have taken the spotlight in unveiling Jaminga's high-energy secrets, X-ray observatories have played an equally vital and deeply complementary role in decoding this mysterious pulsar. The gamma-ray glow may be Jaminga's loudest voice, but its softer X-ray whisper tells us a different, incredibly rich story, one that speaks not only of the pulsar's surface, but also of the physics that govern its life, its environment, and its ghostly trails through space. And leading that charge are some of the most sophisticated X-ray eyes humanity has ever placed in orbit, Chandra and Newton. The Chandra X-ray Observatory, launched by NASA in 1999, is renowned for its unparalleled spatial resolution. Its sharp imaging capability, more precise than any other X-ray telescope before or since, has allowed astronomers to look at Jaminga not just as a single glowing point, but as a complex structure embedded in a dynamic cosmic neighborhood. With Chandra, Jaminga could be observed in stunning detail, making visible structures that would have been mere blurs to earlier instruments. One of Chandra's first major contributions was in mapping the Pulsar Wind Nebula, PWN, around Jaminga. Unlike in the radio or gamma-ray bands, X-rays can reveal the faint, extended emission from the cloud of high-energy particles streaming away from the pulsar. Chandra's observations uncovered elongated tails trailing Jaminga, faint but definite structures, stretching behind it as it speeds through the interstellar medium. These tails, or X-ray jets, appear to result from Jaminga's supersonic motion through space, pushing out a wind of relativistic particles that interact with the surrounding gas and magnetic fields. Not only do these features help illustrate Jaminga's sheer velocity, but they also inform us about the direction of its motion and the pressure of the interstellar medium it plows through. The trails are not perfectly straight. They curve and bend, suggesting complex interactions with magnetic fields and density gradients in the interstellar environment. Chandra's ability to resolve these narrow, faint structures is what made these discoveries possible. Equally impressive are the contributions of Newton, the European Space Agency's flagship X-ray observatory launched in the same year as Chandra. While Chandra specializes in resolution, Newton brings unmatched sensitivity and a broader field of view. Its instruments can collect more photons over time, which is crucial when observing the faint, diffuse emissions from the cooler surface of a neutron star like Jaminga. Newton excels at long-term timing studies and broadband spectroscopy, helping us map the temperature and chemical composition of the neutron star's surface, as well as the surrounding nebula. Thanks to XMM Newton, astronomers have been able to confirm that Jaminga's X-ray emission is not uniform. It consists of multiple components, a soft thermal component that likely originates from the hot surface of the neutron star, and a hard non-thermal component attributed to magnetospheric activity or particle acceleration in the surrounding PWN. This distinction is critical. By separating thermal from non-thermal emissions, scientists can infer the surface temperature and even estimate cooling rates, giving insight into the internal composition of the neutron star, its crust, and its core. The soft X-rays emitted by Jaminga's surface offer a clue to its age and internal evolution. Over time, neutron stars cool, and by modeling Jaminga's thermal spectrum, astronomers estimate that its surface temperature is in the range of a few 100,000 Kelvin. These values agree with the established age of approximately 300,000 years, placing Jaminga in an intermediate cooling phase. Not too young, not too cold. That data feeds directly into neutron star thermal evolution models, helping to refine our theories about nuclear matter at ultra-high densities, conditions that can't be replicated on Earth. XMM Newton's timing precision also allows researchers to measure Jaminga's spin period and spin-down rate with exquisite detail. The observatory has helped refine its rotation period to 237 milliseconds and tracked how that spin slows down over time. These measurements are crucial, not only for confirming Jaminga's identity as a pulsar, but also for estimating its magnetic field strength, age, and energy output. Interestingly, Jaminga's slowdown rate is relatively modest, indicating that while it is still an energetic pulsar, it's gradually mellowing as it continues to age. Another striking advantage of X-ray mapping is its ability to probe anisotropies, variations in brightness or temperature across the neutron star's surface. These could be caused by magnetic field hotspots, residual heat from the original supernova explosion, or localized particle bombardment from the magnetosphere. Some X-ray observations hint at such inhomogeneities on Jaminga, although confirming them would require longer observations with even higher resolution. Still, even this early evidence adds another layer of complexity to the picture. Importantly, both Chandra and XMM Newton have worked in tandem with each other, and with observatories and other bands, to produce multi-wavelength portraits of Jaminga that are far more complete than any single mission could provide. For example, combining Chandra's high-resolution imaging with XMM Newton's deep spectroscopic capabilities enables researchers to correlate spatial features with energy distributions, like associating a hot spot with a spike in hard X-rays or connecting a tail feature with a shift in spectral index. Beyond structural and spectral insights, X-ray mapping has also allowed researchers to place constraints on Jaminga's emission geometry. By analyzing pulse profiles in the X-ray band, scientists can model how the orientation of Jaminga's magnetic and rotational axes aligns relative to Earth. These models are essential for understanding why Jaminga's radio emission is missing. If the geometry is such that the radio beam sweeps away from Earth, it would explain the silence without requiring any exotic physics. X-ray timing has even suggested hints of irregularities in Jaminga's rotation, tiny departures from the expected pulse intervals that might point to timing noise or even glitches. These sudden changes in rotational speed are thought to result from internal rearrangements of the neutron star's superfluid core. Catching such glitches is rare, but when they happen, they offer invaluable clues about the internal structure of neutron stars, how superfluids behave under crushing gravity, how crust-core interactions play out, and how angular momentum is conserved. In essence, Chandra and XMM Newton have transformed Jaminga from a nameless gamma-ray dot on the sky into a dynamic, evolving astrophysical laboratory. Their data have revealed a pulsar in motion, cooling, aging, accelerating particles, and sculpting its environment. They've mapped its trails, characterized its emissions, and timed its heartbeat. Most importantly, they've made it clear that even in silence, Jaminga has much to say. Despite its reputation as a radio-silent enigma, Jaminga's story hasn't been entirely devoid of radio whispers. In fact, over the decades since its confirmation as a pulsar, the scientific community has engaged in a long, nuanced debate over one question that refuses to go away: is Jaminga truly silent in the radio spectrum? Some astronomers would argue no. A few tantalizing clues have emerged, suggesting that Jaminga may not be completely mute, just exceptionally quiet or shy in the radio band. These marginal detections, fleeting and controversial, have become an area of persistent curiosity. They hint that the reality might be more complicated than a simple yes or no. In the early 1990s, following the identification of Geminga as a gamma-ray and X-ray pulsar, a number of teams around the world began searching earnestly for radio emissions at Geminga's coordinates. For the most part, their efforts came up empty. But in 1997, a glimmer of something unusual caught the attention of a group working at the Very Large Array, VLA, in New Mexico. They reported detecting a faint, pulse radio signal from the direction of Jaminga at a frequency of 102 MHz. This wasn't just noise, it appeared to match Jaminga's rotation period, which was already well documented in the X-ray and gamma-ray regimes. The finding was cautiously published, triggering both excitement and skepticism. Other groups attempted to replicate the detection at different observatories and frequencies. Some followed up at 111 MHz and 610 MHz, and while a few reported similarly faint hints of pulsed radio signals, others were unable to confirm the result. This inconsistency led to a frustrating back and forth in the scientific literature, one camp seeing tentative confirmation, another unable to see anything at all. It was a reminder of how delicate these measurements can be when dealing with sources that are not only distant and faint, but also embedded in a sea of galactic background noise. Several factors could contribute to these mixed results. One is the possibility of intermittent emission. In some pulsars, particularly those classified as nullars or intermittents, radio pulses may disappear for minutes, hours, or even days before returning. If Jaminga were such a pulsar, then any attempt to observe it during a quiet phase would naturally yield nothing. Timing and luck would play a huge role in successful detection. Another possibility is extremely narrow beaming. If the radio beam from Jaminga is so tightly collimated that Earth only grazes its edge on rare occasions, then the signal would be exceptionally weak and sporadic. That could explain why the detection seems to flicker. Sometimes just enough signal is seen to suggest presence, and other times it falls below the noise threshold entirely. This idea finds some support in the broader modeling of Jaminga's beaming geometry, which we discussed earlier. There's also the matter of frequency dependence. Pulsars are not uniform in how they emit radio waves. Some shine more brightly at low frequencies, while others are more visible at higher ones. It's possible that Jaminga emits at frequencies that have rarely been probed with the required sensitivity. Or perhaps the emission lies in a narrow frequency window that has been overlooked in many surveys. Radio telescopes like LOFAR, Low Frequency Array, and the GMRT, Giant Meter Wave Radio Telescope, have become instrumental in probing these lower frequencies with higher sensitivity than was previously available. While neither has provided definitive proof of Jaminga's radio voice, they have significantly advanced our ability to say with confidence what isn't there. Yet even non-detections provide value. They help constrain theoretical models, narrowing down the parameter space for possible emission mechanisms. Skeptics, meanwhile, have good reason to doubt the marginal detections. In radio astronomy, especially at low frequencies, the risk of false positives is high. Atmospheric interference, radio frequency interference, RFI, from human technology, and instrumental noise can all mimic weak pulse signals. Without repeatable and statistically robust confirmation, any single detection must be viewed with caution. The standards for claiming a new pulsar, or even a faint radio component, are justifiably rigorous. Despite this, some theorists are hesitant to completely shut the door on the idea of a radio-emitting Jaminga. They propose that Jaminga may not be radio silent in the absolute sense, but radio hidden. That is, the mechanisms for radio emission may still be present, but they operate under unusual conditions, perhaps modulated by magnetic anomalies, spin-axis drift, or exotic plasma effects in the magnetosphere. If this is the case, then occasional, borderline visible emissions could occur under very specific alignments or magnetospheric states, making them incredibly difficult to catch. This has opened up interesting new lines of inquiry, including the search for off-beam radio emission, weak radio emissions that do not align with the main pulse beam but might still be scattered or emitted from side lobes or other parts of the magnetosphere. These emissions would be so weak that they could be buried under noise unless one knew exactly what to look for and when. Intriguingly, Jaminga is not the only pulsar with this kind of mystery surrounding it. A few other pulsars, like PSR J1836 plus 5925 and PSR J0007 plus 7303, exhibit similar properties, strong gamma-ray pulses with little or no radio counterpart. These radio-quiet gamma-ray pulsars form a growing subclass that challenges traditional pulsar categorization. They suggest that there may be a broader family of neutron stars whose emission is dominated by high-energy processes, and whose radio beams are faint, misaligned, or suppressed. What remains fascinating is that this debate about Jaminga's radio silence hasn't been conclusively settled, even after decades of scrutiny. That alone tells us something profound. Our models of pulsar emission, while robust in many respects, still contain gaps, areas where nature refuses to follow the script. Jaminga exists in that liminal space, perched at the boundary between discovery and mystery, noise and signal, presence and absence. It's poetic in a way. A pulsar known for its silence may yet have a whisper. And in that whisper, hidden beneath the hiss of cosmic static, may lie the key to understanding not just Jaminga, but a whole new mode of stellar expression, one that speaks softly, in the language of probability and paradox. The case of Jaminga is far more than an isolated curiosity in the night sky. It is a direct challenge to the very framework that astrophysicists have built to understand pulsars for over half a century. It undermines assumptions, stretches models to their limits, and whispers the uncomfortable truth that even in an era of precision astronomy, nature can still outwit us with elegance and silence. Pulsars, by traditional definition, are neutron stars that emit beams of electromagnetic radiation, most notably in the radio spectrum, as they rotate. The iconic lighthouse model has guided generations of pulsar research. We understood how the powerful magnetic fields of these rapidly spinning neutron stars could channel particles along magnetic poles, generating beams of radio waves that sweep across the cosmos. The predictability of this model, and the reliability of radio telescopes in identifying new pulsars, made radio observations the gold standard. Thousands of pulsars have been discovered this way, creating a statistical landscape of their life cycles, magnetic fields, and spin-down rates. And then came Jaminga. It didn't play by those rules. Jaminga screamed in gamma rays and glowed in X-rays, yet refused to speak in radio. This wasn't just a deviation. It was a defiance of the standard pulsar narrative. If a neutron star could exist and pulsate so vividly at high energies without a corresponding radio signal, then the radio emission mechanism couldn't be as universal as once thought. That means our understanding of where and how these beams form, especially within the complex structure of a pulsar's magnetosphere, might be incomplete, or even fundamentally flawed. One immediate implication is that radio emission might not be a guaranteed byproduct of pulsar mechanics. Maybe it requires very specific environmental conditions Jaminga doesn't satisfy. Alternatively, the emission might exist but escape in directions we cannot see, or under frequencies we haven't examined with enough sensitivity. All of these possibilities suggest that many neutron stars could be out there, undetected and misclassified, not because they are missing, but because our instruments and expectations are poorly aligned with their true nature. Jaminga challenges the very definitions we use in astrophysics. If pulsars can be so radio quiet, then pulsar, as a category, starts to blur. Do we still define them by the detection method, radio, or by the object itself, a spinning, magnetized neutron star? If the latter, then our census of pulsars in the Milky Way may be dramatically incomplete. What we think of as pulsar deserts, regions of the sky with few detections, could instead be rich fields of undetected neutron stars. They might simply be beaming gamma rays or X-rays, like Jaminga, just beyond the limits of our older instruments. There's also the matter of beaming geometry. In traditional models, radio beams are thought to be broad, often sweeping wide angles as the star rotates. Jaminga hints that this assumption may not hold universally. It may have an exceptionally narrow beam, or its emission axis may be significantly misaligned with Earth. This forces a reevaluation of statistical models predicting how many neutron stars should be observable based on beam width and orientation. A narrower beam means fewer detections from Earth, implying that our current pulsar population samples could be biased. In practical terms, this matters greatly. Pulsars are not just exotic cosmic oddities, they are tools. Scientists use them to test the laws of physics under extreme conditions, to study gravitational waves, and even to navigate spacecraft through deep space, thanks to pulsar timing arrays. If we are only detecting a biased subset of the total population, those that shout in radio, then our inferences about neutron stars as a whole might be skewed. Geminga also disrupts models of particle acceleration in neutron star magnetospheres. Traditional theories place the radio emission region near the magnetic poles, relatively close to the star's surface, whereas high-energy gamma rays are believed to originate further out, possibly near the light cylinder, the imaginary cylinder where the co-rotation speed equals the speed of light. If Jaminga emits strongly at high energies but not in radio, it may mean that its radio generation region is inactive, misaligned, or structurally different. Perhaps its magnetic field is distorted, or its rotation axis has shifted due to internal dynamics or a glitch event. These questions open new pathways for modeling how energy flows and dissipates in the bizarre, ultra-dense environments of neutron stars. Furthermore, Jaminga adds complexity to population synthesis models, those that simulate the birth, life, and death of pulsars throughout galactic history. Models that assume all pulsars are radio loud are clearly flawed. Adjusting those models to accommodate a broader range of emission characteristics, radio loud, radio quiet, gamma only, changes estimates for everything from birth rates of neutron stars to their contribution to cosmic ray production and interstellar feedback. And speaking of cosmic rays, the peculiar silence of Jaminga doesn't reduce its potential importance as a cosmic ray accelerator. In fact, its high-energy emissions suggest that it's an incredibly efficient particle accelerator, perhaps even more so than its radio-loud cousins. This raises yet another paradigm shift, that radio loudness and acceleration efficiency may not be strongly correlated. Some of the most powerful astrophysical engines may be the quietest in traditional wavelengths. Jaminga's existence also underscores the limitations of our observational tools and methodologies. For decades, it was an unassociated gamma ray source, a puzzle piece with no picture. It took decades of improvement in detection sensitivity, computing power, and telescope design to finally unravel it. This suggests that more Jaminga-like objects could still be out there, hiding in the data, labeled as unidentified sources, by gamma ray catalogs or dismissed as background noise. As newer instruments like the Square Kilometer Array, SKA, enhanced gamma ray observatories, and next-gen X-ray telescopes come online, we may finally begin to unearth this hidden population. But all of this also carries a deeper implication about the philosophy of science itself. Jaminga teaches us that our models are only as good as the phenomena they can explain. When nature gives us an outlier, we must not dismiss it as an exception, but embrace it as a revision note from the universe. Every silent pulsar, every misaligned beam, every marginal detection that doesn't fit the mold, these are clues that the universe is more intricate, more layered, more nuanced than our theories predict. Jaminga, in all its silent brilliance, reminds us that science is not a final verdict, but a continuous dialogue between curiosity and the cosmos. It challenges our understanding, but in doing so, it deepens it. And in its silence, it asks louder questions than many stars that scream in every wavelength. Modeling pulsar magnetospheres has always been a complex challenge in astrophysics, requiring a delicate balance of observation, mathematics, and theoretical creativity. In many ways, the discovery and continued study of Jaminga has served as a catalyst for this modeling evolution, forcing scientists to confront the limits of current frameworks and push beyond them. Because Jaminga does not emit detectable radio pulses but radiates powerfully in gamma rays and X-rays, it provides a rare and valuable opportunity to refine our understanding of how pulsar magnetospheres are structured and how their emission mechanisms truly work. A pulsar's magnetosphere is the region around the neutron star that is dominated by its intense magnetic field. For most pulsars, this field is assumed to be dipolar, like a bar magnet, with two magnetic poles from which radiation can emerge. Charged particles accelerate along the field lines and emit radiation through synchrotron or curvature processes. This setup gives rise to the familiar lighthouse effect, where beams of radiation sweep across space as the star spins. But Jaminga throws a wrench into this idealized picture. If we cannot detect its radio beam, and yet we observe sharp, periodic gamma-ray and X-ray pulses, then the structure of its magnetosphere must be atypical or at least more complex than the standard dipole model. This forces theorists to examine regions of the magnetosphere that were previously overlooked or simplified in simulations. One major development stemming from Geminga-like pulsars is the outer gap model. In this model, the high-energy gamma-ray emission does not originate near the neutron star's surface, as radio emission typically does, but rather from gaps in the magnetosphere located near the light cylinder, the boundary where the co-rotation speed of the magnetosphere would reach the speed of light. These outer gaps are vacuum regions where electric fields can accelerate particles to extremely high energies, leading to gamma-ray emission. The fact that Jaminga shines so brightly in gamma rays is strong evidence supporting this model. It tells us that particle acceleration and emission can occur far from the star's surface, and that the mechanisms involved may be quite distinct from those responsible for radio waves. Other models, such as the slot gap, or two-pole caustic models, propose similar high-altitude emission zones that wrap around the magnetic axis. In these frameworks, the light we see is shaped not only by where it originates, but also by how it is bent and delayed by relativistic effects, such as aberration and time-of-flight delays. The result is a complicated dance of light paths and beam shapes that depend on the star's spin, magnetic geometry, and orientation relative to Earth. Jaminga's peculiarities provide a real-world testbed for all these models. Its pulse profile, the way its gamma-ray light curve appears over time, can be compared against simulated profiles generated by different magnetospheric structures. In fact, this method has been used by researchers using data from Fermi and earlier missions to reverse engineer the most likely beam geometries for Jaminga. These reconstructions suggest a significant misalignment between the spin axis and the magnetic axis, as well as a narrow beam that may be visible only in certain high-energy bands. This has also influenced the debate on whether the magnetosphere is best modeled as a vacuum or a force-free zone. In the vacuum model, magnetic field lines dominate, and the presence of plasma is ignored. In contrast, force-free models assume a dense plasma environment where electric fields are shorted out by freely moving charges. Observations of Jaminga support a hybrid view. Parts of the magnetosphere may be force-free, while other regions such as gaps allow acceleration and radiation. This hybrid approach is increasingly accepted as more data from objects like Jaminga become available. Another major implication involves the concept of magnetic multipoles. While most models assume a simple dipole structure, there is growing evidence that neutron stars may have complex magnetic fields with quadrupole, or even octupole components. These higher-order fields decay more rapidly with distance, but they could have profound effects on near-surface phenomena, including the creation or suppression of radio beams. Jaminga's radio silence may, in fact, be caused by local magnetic anomalies that disrupt the usual particle flow or beam structure near its poles. Then there's the plasma itself, the ionized soup of electrons and positrons that fills the magnetosphere. In most radio-loud pulsars, this plasma plays a crucial role in generating coherent radio waves through mechanisms like curvature radiation or plasma instabilities. But if Jaminga lacks such plasma near its poles, or if the plasma density is below the threshold required for coherent radio emission, then it could explain the radio silence without invoking beam geometry. Modeling this plasma behavior, especially under the extreme gravitational and magnetic conditions near a neutron star, is an ongoing frontier in pulsar astrophysics. And Jaminga serves as a reminder that the parameters we assume for these models may need to be broader, or even redefined. Moreover, general relativistic effects must be considered when modeling such extreme environments. The immense gravity of a neutron star warps spacetime, bending the path of outgoing radiation and altering our perspective of where emission zones are located. This means that gamma rays we detect from Jaminga may not be coming from the regions we assume based on Newtonian physics. Incorporating general relativity into magnetospheric models has added layers of complexity, but also accuracy, when matching theoretical predictions to observational data. Interestingly, Jaminga's spin-down rate, the gradual slowing of its rotation, provides indirect information about its magnetic field strength and configuration. As the neutron star loses rotational energy, that energy must be going somewhere. In radio-loud pulsars, some of it escapes via radio waves and particle winds. In Geminga, however, the bulk of that energy seems to be channeled into high-energy emission and a strong pulsar wind. The modeling of how that energy is partitioned, and how it escapes the magnetosphere, is intimately tied to our understanding of its magnetic structure. In summary, Jaminga has pushed researchers to move beyond the simplistic, one-size-fits-all model of pulsar magnetospheres. It urges a multidimensional approach, one that accounts for beam geometry, plasma density, emission altitude, relativistic effects, and magnetic complexity. It's no longer sufficient to classify pulsars by what we see. We must now imagine what we cannot. Jaminga may be invisible in radio, but it has illuminated some of the darkest, most puzzling corners of pulsar theory. Before it became the enigmatic gamma-ray whisperer we know today, Jaminga was something far more familiar, though no less awe-inspiring. It was once a massive star, likely more than 8 times the mass of our Sun. Such stars burn brightly and live fast, consuming their nuclear fuel at a breakneck pace. When the fusion furnace in their core runs out of fuel, primarily iron, which cannot be fused into heavier elements without expending energy, the outward pressure that has been holding gravity at bay collapses. In a fraction of a second, the star's core implodes under its own weight, triggering one of the most violent and energetic events in the cosmos, a supernova. This is the birthplace of neutron stars. These are the ghosts left behind from the deaths of massive stars, city-sized remnants of stellar cores that contain more mass than the Sun, squeezed into a sphere just 20 kilometers across. It's almost unfathomable. In a teaspoon of neutron star matter, you'd find more mass than Mount Everest. Jaminga is one of these stellar ghosts. Its past is written not just in its spin and radiation, but also in the trail it leaves behind, a trail both literal, in the form of its pulsar wind, and metaphorical, as a relic of cosmic death and rebirth. Although we never observed the supernova that created Jaminga, we know it must have happened around 300,000 years ago, give or take a few thousand years. That may sound ancient by human standards, but in cosmic terms, Jaminga is still young, an adolescent among neutron stars. What's puzzling is that there's no historical record of this explosion. No supernova remnant is clearly visible around Jaminga. No expanding cloud of gas or glowing filamentary arcs remain in our telescope's field of view. It's as though the explosion that gave birth to it has already faded from sight, like the footprints of a giant that vanished into the night. There are several possible explanations for the missing remnants. One is simply that, with 300,000 years to disperse, the supernova's shockwave and debris have long since blended into the surrounding interstellar medium. The explosion might have swept through a low-density region of space, allowing the materials to expand rapidly and become so diffuse that they are now essentially undetectable. Another possibility is that we're just not looking in the right wavelength. While some remnants glow in optical or X-ray light, others might only be detectable in radio or infrared, hidden behind veils of dust and gas. The truth is, space is a noisy, complex place, and supernova remnants don't last forever. Even without direct evidence of the original explosion, Jaminga's properties offer tantalizing clues about its progenitor. For instance, its high velocity through space, estimated at hundreds of kilometers per second, is likely a result of an asymmetric kick it received during the supernova. These natal kicks are common among neutron stars and are caused by uneven forces during the explosion. In essence, the blast wasn't perfectly centered, and that imbalance gave Jaminga a shove through the galaxy. This has left it speeding away from its birthplace, carrying with it the story of a massive star's collapse, frozen into motion and encoded in every pulse of high-energy light. Interestingly, Jaminga's name, meaning, "It's not there," in Milanese dialect, could not be more ironic. Because in truth it is there. It's the dense, glowing ember of a long-dead star, hiding in plain sight. It no longer shines with the brilliance of a young massive star, nor does it throw off the billowing gas clouds of a newly formed supernova remnant. What remains is subtler, quieter, but no less profound, a spinning beacon, whispering across the void with messages in gamma rays and X-rays. It's what astronomers call a middle-aged pulsar, and yet it still bears the energy of its cataclysmic birth. There's also a tantalizing connection to Earth's own cosmic environment. Some researchers have speculated that Jaminga's explosion might have had effects even here, on our planet. While 800 light-years is not particularly close on a galactic scale, it's also not all that far. If its progenitor supernova had occurred just a bit closer, or if its shockwave had been particularly intense, it could have bathed Earth in high-energy radiation, potentially even affecting life. Studies of isotopes found in ancient ocean sediments have revealed spikes in radioactive materials that could be linked to past nearby supernovae, though there's no definitive link to Geminga specifically. Still, the idea that Earth may have felt the tremors of this ancient death event is a powerful reminder of the cosmic forces that surround us. Moreover, the absence of a remnant around Jaminga raises broader questions about the life cycle of supernovae. How many other neutron stars might exist that, like Jaminga, are moving silently through the galaxy, their birth cries long since faded? For every supernova we observe, there may be many more that escaped our detection or happened before humans even existed. Jaminga represents a class of objects whose origins are cloaked in darkness, stellar phantoms whose past must be inferred through indirect science, careful measurements, and astrophysical detective work. The birth of Jaminga was an act of violent beauty, an end that seeded a new kind of existence. No longer a star in the traditional sense, it became something arguably more mysterious, a rotating beacon of extreme physics, a carrier of secrets from the core of a once mighty sun. It's a fossil of a supernova, not in stone, but in space-time, in magnetism, velocity, and decay. The fact that we can detect its heartbeat at all is a testament to the power of modern astronomy, and the enduring brilliance of things long thought extinguished. The pulsar family is far from monolithic. In fact, Jaminga belongs to a vast and varied menagerie of stellar remnants, a veritable pulsar zoo filled with strange and exotic creatures, each exhibiting behaviors as unique as the cosmic circumstances that gave rise to them. And understanding Jaminga becomes even more fascinating when we view it in this broader context. Like a silent cat prowling among a cacophony of barking dogs, Jaminga's radio silence contrasts starkly with the more vocal members of its kin, drawing our attention to the diversity of neutron star manifestations. Most pulsars are discovered via their radio emissions, blinking in rhythmic beats as their beams of energy sweep past Earth like the light from a cosmic lighthouse. These, normal, pulsars often spin with periods between about 0.1 to 1 second and slowly lose rotational energy over time, gradually spinning down as their electromagnetic radiation drains their angular momentum. But outside of this standard model, we find more extreme varieties, each bending the rules in unique ways. Take magnetars, for instance, perhaps the most terrifying members of the pulsar zoo. These are neutron stars with magnetic fields 1,000 times stronger than ordinary pulsars and over 1,000,000,000 times stronger than Earth's. When a magnetar twists or cracks its own magnetic field, a process called a starquake, it can unleash enormous flares of X-rays and gamma rays. These flares can be so powerful that they momentarily affect Earth's upper atmosphere, even from distances of tens of thousands of light-years. Unlike Jaminga, which is consistent and relatively subdued in its emissions, magnetars are volatile and temperamental, their brilliance peaking in bursts of violent radiance. Then there are millisecond pulsars, ancient neutron stars that spin with astonishing speed, often rotating hundreds of times per second. These objects are thought to be recycled pulsars, spun up by accreting matter from a binary companion. As material from the nearby star spirals onto the neutron star, it transfers angular momentum, gradually increasing the pulsar's spin rate. The result is a time-keeping marvel. Some millisecond pulsars are so stable they rival the precision of atomic clocks. Unlike Jaminga, which spins every 237 milliseconds and emits mainly high-energy photons, millisecond pulsars are masters of consistency in the radio band. Other peculiar members of the zoo include intermittent pulsars, objects that seem to turn their emissions on and off, sometimes disappearing for weeks or months before reappearing without warning. There are also nulling pulsars, which abruptly stop pulsing for a few rotations, and rotating radio transients, RATs, which emit sporadic bursts of radio waves instead of regular pulses. These unpredictable behaviors complicate the task of identifying pulsars and add more texture to our understanding of the neutron star population. Could Geminga be related to these oddballs in some way? Is it possible that its radio silence is part of an intermittent or transient pattern we haven't yet observed over a long enough timeline? Even more bizarre are the so-called central compact objects, CCOs, neutron stars found in the centers of supernova remnants but showing no detectable radio, optical, or gamma-ray emission. These enigmatic bodies radiate primarily in X-rays and have unusually low magnetic fields. They're sometimes dubbed anti-magnetars, existing at the opposite extreme of the magnetar spectrum. While Jaminga has a moderately strong magnetic field typical of normal pulsars, its lack of radio emissions and gamma-ray dominance place it closer in spirit to these odd, quiet anomalies than to its vocal radio-loud brethren. There are also pulsars in binary systems, where the interplay of gravity and radiation leads to fascinating phenomena. Binary pulsars can exhibit gravitational lensing, tidal distortion, or even orbital decay due to gravitational wave emission, a phenomenon directly observed in systems like the Hulse-Taylor binary. Some pulsars even orbit black holes, forming astrophysical laboratories for studying extreme gravity. Though Jaminga appears to be solitary now, it's not impossible that it once had a companion, a star disrupted or absorbed during or after the supernova event. Even among isolated pulsars, there's remarkable variety. Some young neutron stars are seen surrounded by pulsar wind nebulae, structures formed by the relativistic wind of particles streaming from the pulsar's magnetic poles, creating glowing halos in X-rays and radio. Jaminga has its own trail and bow shock, but it lacks a luminous nebula like the Crab or Vela pulsars. Instead, it quietly glides through space with a faint but clear X-ray tail, providing a different flavor of observational evidence for its rapid motion and energetic past. What makes Jaminga especially intriguing is that it doesn't quite fit neatly into any one category. It's not a magnetar, though it's bright in gamma rays. It's not a millisecond pulsar, though it spins fast enough to be of interest. It's not a central compact object, though it's radio quiet and X-ray bright. It shares features with several categories, yet stubbornly resists full classification under any single label. It's as though nature crafted Jaminga with a bit of everything, then muted its voice, forcing us to decode it in silence. This pulsar zoo helps illustrate how neutron stars, though born through similar means, can evolve down radically different paths. Differences in initial mass, magnetic field strength, spin rate, environment, and binary history all shape what a neutron star becomes. Jaminga's path led it to be one of the rarest breeds, a radio-quiet gamma-ray pulsar, with characteristics that offer both puzzles and insights into the inner workings of stellar death and compact object evolution. Moreover, the existence of such diversity forces us to reconsider our search strategies. If our tools and surveys are tuned only to radio frequencies, we risk overlooking entire populations of neutron stars like Jaminga. It's like trying to catalog birds using only sound, and assuming that any silent creature must not exist. Jaminga reminds us that the universe often speaks in frequencies we weren't initially listening to, and that silence is not absence, but another language. As our telescopes grow more sensitive across all wavelengths, from radio to gamma rays, from gravitational waves to neutrinos, the pulsar zoo is bound to expand. New categories may emerge, old ones may blur, and Jaminga, in all its silent brilliance, will continue to be a key figure in this cosmic bestiary, a benchmark for what's possible when a neutron star defies the rules, and teaches us to look beyond the obvious. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.